be fine. It should be fine. Ah, so that was your problem. Okay. Yeah, I'm using LibreOffice because I'm trying to be different.
Hello, hello.
If Andres Suhl is in the room, please come to the front to test your presentation setup. Andres Suhl, please come to the front.
Hello. So hello everyone, my name is Stefan. I'm your session chair for today's first session, and we have 3 wonderful papers today. And the first paper we going to hear about is called Warp Level Culling for Efficient Blending in 3D Gaussian Splatting. The authors are Kenneth Young, George Dutakis, and Gilbert Bernstein, and Kenneth will be presenting. Take it away, Kenneth.
All right, hello. Good morning. My name is Kenneth Young. I'm from the University of Washington, and I'll be here to talk to you about warp level culling for efficient blending in 3D Gaussian splatting. So that's a lot of words. What does that mean? So essentially, in 3 lines here, 3D Gaussian splatting is important. We made the rendering pipeline faster, and we did so without changing the image output whatsoever. So that gives you a sense of what I'm going to be sharing with you today. So in this talk, we're going to break this down to 3 steps. We're going to talk about first, how much faster did we make the 3D Gaussian splatting rendering pipeline? How do we know we could do that? And then finally, what exactly were the steps we took to achieve this? So let's start with how much faster do we make the pipeline? Here, we demonstrate we have a 19% increase in frames per second on the 4090 and a wider 32% increase in FPS on the 2070 Super over the state-of-the-art differentiable rendering techniques that don't compromise on visual quality. So what does this visual quality thing mean? So we categorize ourselves in the space of 3D Gaussian splatting renderers that use the alpha over blending technique to render the splats. So alpha over blending is the exact solution to rendering semi-transparent surfaces, and this is the kind of techniques that we work with. So here we're showing 3D Gaussian splatting by Kerbal et al., which is the original algorithm for doing this. TCGS by Liao et al. Is another technique that uses tensor cores on the GPU to compute the alpha over blending faster. And FlashGS by Feng et al. And FasterGS by Halbaum et al. Do some combination of like smarter boundary and occlusion checks to ensure that only splats that contribute to the final image actually get loaded. And so these are different ways that they get around making the blending system, the rendering pipeline faster without actually deviating from the alpha over blending technique. And so one extra thing I want to emphasize here is that with our technique, FasterGS is the state of the art in this system, and so we're building on top of FasterGS. And because of this, we actually show that we have a bit identical output to FasterGS. This is a pretty boring slide because it's the same image over, but our optimizations that we add, you can put this on any other algorithm, and you get the exact same image output just with the FPS increase. Okay, so now that we set the stage on like how much faster we're talking about here, what kind of speed as we get, let's talk about how do we know we could do this, and how do we know we could make these improvements? So we're focusing on the rendering pipeline, right? And so here is the rendering, a rough timeline of what the rendering pipeline looks like in FasterGS. This is roughly the same pipeline that any sort of rendering system that uses the alpha over blending technique uses. And there's essentially 4 stages here. You start with pre-processing, which is where you take the 3D Gaussians from the model file and you project them onto the screen to create your 2D splats for rendering. Then this goes over to a sorting stage to do depth sorting for these splats. This is required for the alpha over blending. And then after that, you would distribute your splats over into the GPU for tile-based rasterization. Finally, you get to the part where you actually do the alpha over blending. So now you have a bunch of splats that are ordered and you're ready for blending. This weirdly takes a long time because it's just blending, which is a pretty straightforward process. Why does it take a huge part of the actual pipeline? And so this is something that we want to investigate further. So to do that, we're looking at FasterGS's blending kernel, which is that last stage. So FasterGS's blending kernel essentially has 2 distinct stages that happens into it. Let's break this down. So coming off of that distribution stage, we essentially have the image-based, we're doing this tile-based rasterization where we get a subtile of the image that we're going to render. This tile by default is a 16 by 16 pixel tile and is assigned to a 16 by 16 thread block. And so if you notice here, there's like a 1-to-1 mapping of threads to pixels that's being mapped together for rendering. Once we have this arrangement, we go off to the first stage of the kernel, which is to take the 16 by 16 threads, and they're going to collaboratively go out to global memory and fetch 256 splats and bring that into the block's shared memory for processing. So again, there's a 1-to-1 mapping here of threads to splats in this first stage. There's a sync barrier here. Once all the data is fetched from global memory into shared memory, we go on to stage 2, which is where each thread is going to individually go out and iterate through that 256 splats and do the alpha over blending process to create the final pixel color. So that's stage 2. Once you exhaust those 256, if there's still more splats that are assigned to the tile, it goes back out to stage 1 to fetch the next batch. You keep on doing this until you've completed all the splats that are assigned to the image tile. Now you may notice here that we've been working in this space of like single pixels here. This means that there's a bunch of these other splats that are assigned to the image tile that never intersect with the pixel, and they still get processed because they get pulled in and they get like rendered by the second stage, but they end up being rejected because they have 0 contribution to the pixel at all. This seems weird. Maybe we could fix that. Let's hold on to that thought. So now that we see how the blend kernel works, what exactly is our headroom here? How much improvement can we possibly make out of this? One way to quantify this is through a technique known as peak theoretical throughput. Past literature have used some form of this formula right here, and we're going to use a variant of this to help us understand and quantify how much headroom we have in our pipeline, in our kernel. So we compute this by looking at the minimum duration it takes for the blend kernel to run. This is done by looking at the memory load that comes in and out of the kernel and the floating point operations that go on in the kernel. And you divide this by the theoretical throughputs of your GPU. So this is information you get by counting or profiling the kernel construction, and then you can also get GPU specs from the spec sheet. People who are familiar with this technique may have noticed that this is a summation when typically this is actually computed as a maximum or some other combination. And that's because GPUs can typically schedule and interleave the memory load and the compute stages. But for 3D Gaussian splatting, because we have this like specific staged approach, we need to actually make this a summation of these 2 durations, because there is this sync barrier that happens that all the data needs to be pulled into the block's shared memory first before it can be done, before any compute can be done on it. So this is how we formulate the minimum duration of the blend kernel. If you take the reciprocal of the duration, you essentially get like the throughput, the number of times per second this kernel can run, and we can use this to kind of give a sense of how fast this kernel can run. And if you compare this, so what this shows from the theoretical to our this is not abnormal to see a slower actual runtime, but this wide of a gap suggests that there is delays outside of just pure global memory fetches and floating point operations. This suggests things like maybe delays in cache level memory and other things that are happening within the kernel and register space. Cache level memory means shared memory, which is a big important part of the blend kernel. So this basically shows that we have some headroom for improvement, and it may have something to do with the way data is being moved in and out of the kernel. All right. So we've seen how much faster we can go. We've seen that there's some headroom to do that. What exactly did we do to address these issues? So in our paper, we introduced 3 optimizations to FasterGS's pipeline, which again, these can apply to any other alpha overblending rendering techniques. The first is warp level culling, which is the headlining feature. And then the next 2 are smaller adjustments that we made just to the memory flow that specifically target the memory traffic issues that we believe exist. OK, so let's start with warp level culling. As a reminder, this is what FasterGS's blend kernel looks like. There's these 2 stages. And warp level culling takes this, and we're going to add a 3rd stage in between them. This is warp level culling. We're going to step through from left to right and break down what's happening here. Starting from the left, we're going to start with the same place we started with FasterGS, where coming off of the distribution phase, you now have an image tile that you're going to be sent off to GPU for rendering. In this 16 by 16 pixel image tile, we're actually going to subdivide it one more time and into a 4 by 8 pixel subtile, and we're going to assign this to a 32 thread warp. And so this 4 by 8 pixel is 32 pixels. There's a 1-to-1 mapping here. And now we have this subtile of the image tile that we're going to use for rendering. Moving on, we're going to have the same stage 1 where all the threads in the block are going to go fetch the data from global memory, bring that into shared memory because the whole block needs it. And now we're going to introduce a new stage 1.5 in the middle here. This is where we're going to take those 32 threads in the warp, and they're going to collaboratively hit test a mini batch of 32 splats out of shared memory against that little subtile that we assigned just now. What this is going to do is we're going to basically generate a bitmap, essentially a list from this little batch of 32 splats, and decide which of these splats actually have a chance of hitting any of the pixels in this subtile. So now that we have this little subtile, all the pixels in there are going to know the collection of 32 splats here, whether or not they're going to be in the subtile or not. And this is great because then when we go back to stage 2, instead of iterating through all 256 splats from shared memory, we're going to just now look at those 32 splats that we just hit test. And from there, we're going to just render only the ones that pass that hit test. So you'll notice here that the key thing we did here is that now all of these splats that were never going to hit any of the pixels in that little subtile have now been really efficiently just culled away. And at the render stage, you're not actually looking at them anymore. So why is this culling thing so important? Why do I keep on focusing on this? Well, the key thing here is that at the pixel level, at the very last stage when you're going to actually render the color of a splat, you need to pull its alpha, its orientation, and its color from shared memory into kernel space. And then after that, you have to evaluate the extent of the Gaussian to see if it will intersect the pixel at the pixel's location. This evaluation is both memory intensive. You got to pull that data out of shared memory. And also, the Gaussian evaluation is an exponential plus a bunch of other floating point operations. So this is a very expensive computation to do if ultimately you're just going to reject the splat because it has no contribution at all to the pixel. And so by replacing that really expensive step with just a very simple bounding box Boolean intersection test, you essentially get rid of a ton of extra effort that would have gone to waste anyways because you weren't going to render that splat. And so now we've essentially changed all that to just a simple, in this stage 1.5, we changed that into just a bounding box fetch and then a Boolean intersection test with the subtile. So what kind of savings do we get here? We actually see a significant reduction in 32-bit floating point operations from this change alone. And what we're seeing here is essentially not only are we just getting rid of the floating point operations that were tied to doing that computation for evaluating the Gaussian, but we also got rid of all the memory fetches you had to do at the last stage to actually do that computation together. So altogether, we're seeing about 13% frame time improvement with just warp level culling on its own. Okay, now that we have that in there, we have space now for 2 other adjustments that we can use to target the memory things that are left over. With warp level culling, because we're doing things now in batches of 32 splats off of our like shared memory pool, we actually have a logical opportunity here to try adjusting that initial fetch size. Since we're working in batches of 32, we don't actually necessarily have to pull in 256 splats from global memory into the block shared memory. We try something else. So this is a comparison of different fetch sizes and the percent improvements we get over faster GS. At 32 splats off of global memory, this is obviously a pretty small amount. We're not really getting much saturation here. But what's interesting is that if you zoom in on this top end here on the right side of the graph, we actually see that 192 splats for the 4090 and 3090 is actually faster than 256 splats. This was a surprising finding. And the 2070 Super still actually prefers 256, but this is essentially a parameter you can tune per GPU to basically optimize for the GPU's capabilities. And so with this little change here, we get another 8% frame time improvement, which is pretty interesting. Okay, finally, we're going to look at how we can rearrange data in shared memory because we have a lot of interactions with shared memory. Optimizing for that throughput is actually pretty important. On the left here, we have the shared memory organization from FasterGS. Splats, as I mentioned, the data for a splat is the conic and opacity, which is essentially the orientation and its shape and its opacity. We have the position of the splat and also the color of the splat. This is arranged in a 4D vector, a 2D vector, and a 3D vector. Now, what's interesting about 3D vectors is that there's actually no optimized instruction to pull a 3D vector from shared memory. And so this actually gets compiled down to 3 separate floating point pulls. And so if you just simply add padding to this, you actually get a 4D vector. But you get a 4D vector, and that becomes an optimized instruction pull. Finally, the other thing is for the warp level culling, we need the bounding box information to do the hit testing. And this we can basically put into that free space in the 2D vector, and we can put that in there to get data we can pull from shared memory just to do the hit test. Now, the bounding box information is just in screen space, so this can fit in 64 bits of memory. That's fine. Okay, so with that, we get another 5% improvement. So these 3 contributions together form our warp level culling optimization, and this is how we get the speedups without changing any of the image output whatsoever. And another important thing about this is training, which is an important part of 3D Gaussian splatting. So because we don't change the image output at all, training still works, but we didn't really see any improvements when we tried implementing it. This is definitely room for future work to see if there's any advantages, because again, it is compatible with the CUDA rendering pipeline, CUDA training pipeline, and any implementation that uses these contributions can use it. All right, so I'd like to finish up with some acknowledgements. I just finished my master's at the University of Washington, and I'd like to thank Professor Gilbert Bernstein for being my advisor during my undergrad and master's. I'll be continuing on to do my PhD at INRIA with Dr. George Tricotes, who is also funded by the European Union and the ERC. The project source code and contact information can be found at the big QR code, and for those on YouTube, you can find the conference information on the small one. Thank you.
Thanks a lot, Kenneth, for the very nice talk. Are there any questions to Ken?
Hi, it was a great talk. I'm wondering how much, do you need extra computer bounding box for each splat? And would that like extra compute and extra memory of the computing or storing the bounding box actually hurt the performance? And is your number provided is only the rasterization stage, or if you look at the pipeline as a whole?
Yeah, great question. Okay, so the bounding box information actually comes from the pre-processing stage. It's already computed there because that's a part of the culling stage that happens when you're just initially pulling the data off the memory. So computing that is free. The extra work here is carrying that bounding box information through the rest of the pipeline. And so we're essentially doing a little bit of a trade-off here where we're using a little bit more global memory, technically, to do this trade-off. We found that it's worth it, and it didn't change the rest of the pipeline. So FasterGS, their work was very focused on making sure that you reduce the amount of global memory usage at all costs. And this is probably why that they didn't want to carry around this bounding box information. And so there might be some interesting things. There might be some interesting effects with training, because for FasterGS they claim that any memory you add to the global memory affects training negatively, and this could be for future work. But in terms of compute and the rest of the pipeline, it is fine.
We have another question over here.
So it looks like you evaluated the performance just by the runtime performance. Did you look at any of the tools like Insight Graphics to actually confirm there were memory bandwidth advantages? I mentioned that because partly your theoretical analysis made it sound like there was even more headroom, and maybe there are still bottlenecks to explore.
Yeah, thanks. So we actually spent a lot of time in Insight Compute to try to like poke around what's going on. So in the paper, there's like a screenshot of Insight Compute that showed a lot of the basically there was like a lot of warp levels. Sorry, not warp level. What's it called? There were stalls happening at the sync points, and there were stalls happening with the shared memory pools, and some of it was like really difficult to figure out how to get around, because you had to at some point pull that data into the kernel somehow. And so I think there's room for improvement in terms of maybe other ways of arranging how data gets pulled from shared memory. That was a huge bottleneck. And yeah, the theoretical throughput analysis shows there's a huge room for improvement, and we don't meet all of that yet. I think the biggest thing here, as with any greedy Gaussian splatting, there's a lot of indirection and memory cache incoherence, because you're pulling the splat data from all over the place in global memory. So that's kind of like other things that you can optimize for that we didn't really get to. Yeah.
Yeah, we still have plenty of time for questions. Are there more questions to Ken? Yeah.
Hello, nice talk. Have you given any go on Android devices? Have you run your experiments with Gaussian splats on Android devices and obtained some data? Yeah.
No, unfortunately, we didn't think about that. We were basically doing everything in just a standard CUDA pipeline. So this is with, yeah, so these are, the algorithms we were looking at were just the ones that use the standard CUDA training pipeline. And yeah, so we were just using NVIDIA GPUs for this. Yeah.
Okay.
But I should mention that the implementations we did, I guess warp is like an NVIDIA thing, but like any sort of like synchronous unit of 32 threads, which is, I forgot what AMD calls them, but and Intel has a similar concept. These kind of implementations are not tied to any specific platform, but they give you the general concept that you can use.
Thank you. So in the distribute stage of the renderer, there has been some work which made the bounding of the Gaussians tighter than a bounding box, like for example, stop the pop. Have you looked into some of these methods, if they can also be applied subtile? And is it worth it?
Great question. So we didn't look in the distribution stage to see. I have to think more about that to see whether or not it's worth it. It might be, but this was definitely trying to do like a streaming, like at runtime type of behavior where you're at the actual end stage. The key thing here is that we're trying to get rid of that Gaussian evaluation thing that you have to do, which is that exponential you have to compute. Whether or not this can also help with previous stages, my initial like gut feeling is thinking that it might introduce like more effort in those stages where you're just trying to push the data through as fast as you can. But we'll probably think more about that. We can chat about this later, yeah.
Maybe I also have a question. You tested on quite a variety of different GPUs from different periods, and I wonder if there are architectural differences between those GPUs and if this could influence the performance numbers you observe to some sense?
Yeah. This was something that we had like a 2070 Super lying around a 3090 and 4090. That's all we got. And I think the answer is yes, there definitely are architectural differences that probably affected the performance here. I think especially in how the 4090 has like a massive L2 cache, and that like basically that's why we only saw like a small improvement there, because a lot of the effort that we saw was really just pulling things in and out of like shared memory. Pulling things from global memory is like a fixed cost, but all the interaction that happens within the shared memory space is stuff that like GPUs with really nice cache just aren't really going to feel a big difference in. So the older GPUs, like the 2070 Super, which has smaller L2 and also just slower L2, saw a big difference.
I don't see any more hands raised, so let's give Ken another round of applause.
Thank you.
So I think we have Andres here now, right? So.
Do we have HDMI?
There should be HDMI, yes.
Oh, I see.
Yes.
Okay. So let's see.
Very good. So while Andres is still setting up, let me introduce him and his paper. Andres' paper is called Scalable Training and Rendering of 3D Gaussians for Large-Scale Scientific Data. And this paper is by Anders Sewell, Mengyao Han, Shi Wu, and Steve Patrusha. And the presenter is Andres. Take it away.
Thank you. So yes, I'm going to talk about scalable training and rendering of 3D Gaussians for large-scale scientific data. To sort of motivate this work, I feel that it's important to talk about high-performance computing and what a high-performance computer even is. So conceptually, we can imagine having many normal computers that are networked together such that they can combine their compute power to work on a single problem at once. And ideally, this problem would be something larger than you could just do with one single computer, or node in this case. So this is a picture of the Polaris supercomputer. It's located at the Argonne Leadership Computing Facility. When it came out in 2021, it was the 12th fastest supercomputer in the world. As of today, it is the 83rd fastest, which is still quite good. I show a picture of it because it's what I use to do this research with, but just as an example of what a single node of Polaris looks like, you have this server-grade AMD CPU that is connected to these 4 NVIDIA A100 GPUs. The GPUs themselves are connected via NVLink. There's 512 gigabytes of RAM memory, and there are these network interfaces at the top that are for the purposes of networking all of these nodes to every other node so that they can communicate throughout whatever they got to do in working on a shared problem. So why do we build these things? Why do we care about these things? It turns out that we primarily build supercomputers to do really large-scale scientific work. So in this example, this is sort of the worst-case scenario that I could find. This is the exascale or exasky cosmological simulation. It's used to explore dark matter in outer space. So each time step of the simulation can be on the order of about 10 terabytes. So we have this massive compute capability, but our data set, our simulations are being adjusted to account for that. So more complicated things are being simulated. The resolution of the things being simulated are higher. So as a result, we're sort of producing this larger volume of data as things get larger. And it's not feasible to save 10 terabytes of data every single time step, especially if you're going to be simulating for thousands of time steps. So in practice, what ends up happening is as supercomputers get better, as the data volume grows, we end up analyzing or visualizing a smaller proportion overall of the data that we simulate on the supercomputers. And that's a problem, but we have a solution, which is this concept of in situ analysis and visualization, in situ being the Latin phrase for in place. So you can imagine that if we already are running our simulation, so we already have access to this HPC resource, all of our data is already distributed across all of these nodes in the correct way. So the concept is, why don't we just simply perform the analysis or create the visualization that we care about while we already have all that stuff in memory? So this, of course, largely addresses that I/O bottleneck, because instead of saving 10 terabytes of data to disk, you might just be saving some small amount of summary statistics, or even in this case, just one PNG file. So that's a big difference in terms of I/O bandwidth. So this is an example of an image that was rendered by an open source library for doing in situ visualization called Ascent. This was performed in 2018 to sort of exercise the capabilities of both Ascent, but also see what this new Sierra HPC could do. So in 2018, this was the #2 fastest supercomputer in the world. As of today, it is decommissioned. So this image was rendered using 16,000 GPUs across 4,000 nodes, which gives you an idea of the scale involved here. So this image itself is evidence that we have means for rendering these really large data sets already, but notice that we needed 16,000 GPUs to get this single image. So it's not necessarily the case that you would need equivalent HPC resources to visualize your data, but even if you only needed half of this resource, that's still quite a significant amount. And from the perspective of a scientist who's interested in, just seeing the result and going on to the next experiment, this can be quite prohibitive, because if you want to, save this data to disk, let's say, so that you could wait in queue for your time on this shared resource, the supercomputer, even if you wanted just half of this amount, you're going to be waiting a while. And it's no guarantee that you're actually going to be able to render this thing with interactive enough frame rates so that you could really, truly explore it. So what do we do about this? This has sort of been the basis of my PhD work the last couple years, is just exploring whether or not we can explore 3D Gaussian splatting techniques to this problem with the hopes of alleviating this bottleneck in efficiency for scientists, so that they can have sort of a faster pipeline of simulating their data and then being able to explore it quickly and interactively. So, of course, 3D Gaussian splatting, it differs from normal rasterization. We're not using triangles, but we have this collection of Gaussians. And if you have enough of these Gaussians, and if you apply some machine learning magic with good enough ground truth imagery, you can construct these really nice looking photorealistic 3D scenes that are high resolution and also very efficient to render, so in frame rates of excess of, let's say, 60 frames per second. So that's what our interest is here. And it turns out that we're not the first ones to have thought of this idea. There are actually a number of distributed 3D Gaussian splatting pipelines. They're all kind of mostly focused on reconstructing these really large outdoor scenes that span potentially multiple miles. And so there's various differences that they have to consider, like how do they reconstruct the sky in that case? Or on the right, this is a synthetic data set, but on the left, you could imagine that depending on the time that you're capturing this ground truth imagery, maybe the shadows are going to slightly be different. Maybe the sky will have changed a little bit, or a cloud is passing over. So you can imagine that just by nature of having your ground truth imagery be based on the real world, there are these extra considerations that you have to take into account. So the other thing that these existing frameworks tend to do is they care about training this single global 3D Gaussian splat model, which turns out to be not ideal for HPC. And the reason that it's not ideal for HPC, so the technique or the idea is that you can add more GPUs and have them all work on the same problem. And when you do that, you can accelerate the speed at which you can do your single problem to a point. So in order for this to work, you have to synchronize all of these GPUs to some extent, and each GPU has to do a sparse all-to-all communication with every other GPU, meaning you could imagine every GPU has to send or receive some amount of data from every other GPU. So as you add more GPUs, to some extent, yes, you're getting better performance, but you're also increasing this communication overhead that has to occur. And if you're just passing messages, that's one thing. I mean, it does have some overhead associated with it, but particularly if you have to do data transfer as part of this communication, the overhead can become quite expensive. So in the case of keeping these things synchronized, you might be passing around the Gaussian primitives themselves. You might be passing around the training images for the purposes of like load balancing. So yeah, this turns out to not be great at scale. So the basis for this work is just sort of having a little bit of an HPC background and thinking to ourselves, can we borrow existing techniques that work really well for other aspects of HPC and apply them for training these distributed 3D Gaussian splat models in a way that will scale, or I guess in a way that doesn't require this expensive all-to-all communication. So this is sort of oversimplified, but on the left, we could imagine that this is the input that we would receive. So like, at the end of a time step, we have all of this simulation data that is representing the current time step or the current state in the simulation. And the simulation already has done the work for us of decomposing this domain and distributing it across whatever accelerators that we have access to. So I've rendered sort of this magenta transparent face of these spinning models to demonstrate that those are the shared boundaries. So this is actually, I guess this thing on the left is what it would actually look like. But you have these shared boundaries, and within the context of a simulation, you can do sort of your advancing of the data that you have access to up until you hit a shared boundary, where it becomes important to have synchronized data with your peers so that your computations come out correct. So the simulation's already doing this work of decomposing the data and providing you with what are called ghost cells so that your computations can come out correct. And for the purposes of rendering, so like at the end of a time step, if we wanted to do that 16,000 GPU render, what you could do is render each of these individual models separately from the exact same camera view. And this sort of animation in the middle shows you what that would look like. So all of these different pieces are spatially offset from one another with respect to the scene. And you can do this distributed sort-last compositing of all of these individual frames to arrive at this final frame, which is as if you would have rendered all of the data together at once. So this is sort of what motivated our work. And it turns out to work pretty well. So this is just the system diagram from our paper. We expect as input, like whatever a simulation would provide you, the data layout equivalent of what a simulation would provide, which is just a decomposed domain with some amount of ghost cell information. And then in that situation, each GPU can produce its own ground truth for training its own individual 3D Gaussian splat model of whatever that domain data is. Then that same GPU can go on to do the training of the 3D Gaussian splat model for that individual piece. And this rendering part actually isn't required. You don't have to do this while your simulation's running, but if you wanted to, or if you wanted to do it later, the way that you could do it is by rendering all of these individual 3D Gaussian splat models and then compositing them using this sort-last compositing to, in a way, cheat, I guess. So here is a volume data set. This is called Blunt Fin. It's made by NASA or provided by NASA. It's, we artificially, in this case, decomposed it into these 4 domains. And what we see along these shared boundaries as we composite this image, so these are all 3D Gaussian splat models at this point, by the way. What we're seeing here is that each of these individual models actually did learn that extra shared boundary layer where the ghost cells are. And when you render them all together, you have this effect almost of like a doubling of the Gaussians along those boundaries, which is not what you want. So there is actually something that we can do about this. On the left, this is sort of the typical 3D Gaussian splatting formulation where you take the 3D Gaussians and you project them into a flat surface. And if you do that, so this black box is meant to represent like the bounding box of what we care about. So like in this case, it's pretty clear, or like we're able to know exactly what the bounding box is of the region that we care about, excluding the ghost cells. So these Gaussians can have covariance that extend outside of that bounding box, even if their center exists within the bounding box. So it's not sufficient just to cull the Gaussian itself, because then you're throwing away this portion of data that you actually do care about that represents your scene. So we instead switched to using this 3D GUT framework or library, which does a ray tracing formulation of 3D Gaussian splatting. So as these rays are cast or being sampled across the scene, we can just simply reject the fragments that exist outside of this bounding box, which gives us these very nice, perfect flat surfaces of just the thing that we care about. And so this is what that same exact data set looks like, just with that fragment level clipping applied. And so this is sort of a worst case scenario because the volume size in this case is really small. So when you're splitting this into 4 discrete pieces, the proportion of the overall rendered image that is represented by those ghost cells is larger than what you would see if this were a really big volume. So in the fact that this is pretty good at even a small scale, I think this is quite promising. So this is sort of the comparison to other state-of-the-art frameworks that do distributed Gaussian splatting. These, as I mentioned before, they have communication overhead. So what this ends up looking like in practice, Retina.js is just sort of the way that it is implemented is slow, but Grendel.js is a pretty good competitor. So for these small scales, it tends to outperform us in training time, which makes sense because you're adding more GPUs to solve one problem. But there is, at some scale, which in this case seems to be pretty big, but like beyond 64 GPUs roughly, the communication overhead becomes so expensive such that it's becoming untenable. So like in the perspective of in situ, like if you wanted to train this thing at the end of a simulation, you don't want to spend multiple thousands of seconds training. So I guess what is interesting here is that as we add more GPUs to our communication-free training pipeline, the amount of work that each GPU has to do is pretty much constant. But we don't see an increase in training time because each GPU is just doing its own portion of the work. So there's no communication at all, at least with respect to training. There is when it comes to visualization. So PSNR, it's a measure of quality. Even though there are cases where, I mean, overall we have pretty good quality. I would say very competitive quality. Even in cases where Grendel.js outperforms us on quality, the overall quality that we're talking about is in excess of 40 PSNR, which is really quite high. So I think it's an acceptable trade to say our quality is a little bit worse, but our training time is significantly better. And I guess the other thing to note here is that there are two different strategies for training Gaussian splats, so GS and MCMC. And the important thing just to differentiate between them in this case is that MCMC will train a little bit faster, or in some cases significantly faster, than the GS strategy, but in exchange for less PSNR generally. And there's another important benefit, or I guess thing to consider when it comes to GS versus MCMC, which is just that you can save a lot of memory. In the GS formulation, as we're adding more domains, we're training like a full 3D Gaussian splat model, which means the Gaussians are allowed to duplicate as much as necessary to best reconstruct that domain. But in the MCMC strategy, we can apply sort of this global limit of the number of Gaussians that we don't want to exceed, and that allows us to save quite a bit of memory in exchange, again, for less PSNR. So these are, instead of like the typical 3D Gaussian data sets that are compared against, we just took some open scientific volumes. We artificially decomposed them ourselves. We did a bunch of this training and collected all this data. The data is in the paper if you're interested. But these are sort of like the results. So we have fairly good training times, at least with respect to what we're comparing against. Pretty good PSNR. So overall, we feel that this is a viable technique for applying to really large science data sets in the future. One more component that is worth mentioning here that is unique to sort of simulation data is that there's this temporal component where each time step is not that much different from the previous time step. So the concept here is, what if we were to take sort of our first time step and train it to a full quality, and then for every subsequent time step just reuse that model, and it turns out that you can save a ton in training time and not lose that much in terms of PSNR. Notice that this is not out of 0, so the quality is still really quite high, even though the quality is drifting over time. And to work around that, you could just retrain a full quality model periodically. So this is what the results look like. Pretty good. I think I'm probably out of time, so I'll just quickly say for limitations in future work. So it's a big problem that currently all of our models are sort of these full-size things, and so it ends up being in some cases larger than the data itself, which is not ideal. That's exactly what we're trying to undo or fix or work around. We could work on this by using a different representation for the Gaussians themselves. So like instead of one that encodes all of like the spherical harmonics data and the color data, we could use one that instead just encodes like a volume value per Gaussian, and then you could just directly apply a transfer function. We have a prior paper on that came out this year, so it would be better to switch to that. Training time is pretty good compared to state of the art, but for in situ, you wouldn't want to wait more than 7 minutes while your simulation is paused. From a scientist perspective, you would rather the science just go on. Much better techniques exist for compositing. So the paper has the results. I didn't include them here because they're not like particularly great, but we have decent results, but they could be much better if we were to just simply switch to better techniques for distributed compositing. And finally, depending on your perspective, we don't have a single global model that you get at the end as output. You could concatenate two models at a time and then fine-tune them and keep doing that until you end up with one single global model at the end. We just haven't proven that that works. So that's all. Thank you very much.
Thank you very much, Andres. Other questions?
Yeah, thank you for the great talk. That was really interesting and very interesting use case. I have one question about the application itself. Maybe it's also the data set question. So I mean, 3D Gaussian splitting is more of a novel view synthesis algorithm and appearance capture algorithm. So for your use case, wouldn't it be true that maybe somebody wants to play with a model by slicing it and looking into the interior of the model? And in your training strategy, is the interior of the model actually accurately represented, or is it more like an outside view that people care about?
It's a great question. And this sort of runs up against just limitations, or I guess attributes of 3D Gaussian splatting itself. So like if the surface that you're reconstructing is highly opaque, then it's probably not going to learn the internal structures very well. But like in the case of pretty much all of these data sets, we made them slightly transparent so that you actually could learn sort of those internal structures. And when you do that, in my experience, the answer is pretty much yes, that you can learn the internal structures well enough to where if you wanted to slice these things or do whatever type of analysis you would want to do, it would work really well.
Great talk. I might have missed this. What are the rendering speeds of this, and what kind of hardware do you need to see these models?
Very good question. I can't think of rendering speed. Okay, I'm sorry. So like you're talking about the composited rendering. So like if this were 128 individual images, how fast can we render them all as one thing? As a scientist, what are you seeing? Yeah, so the question is if you're a scientist, how do you use this? So in the current formulation, I guess this is more a proof of concept than anything, but if you have this 128 individual 3D Gaussian splat models, you could either render using one GPU every single one and then have one individual frame for all of them and then composite them all together. That would be really slow, but you could at least do that with like a single GPU. Or in the context of HPC, you could request whatever amount of the HPC that you need that gives you enough GPUs to visualize all of these things interactively. So ideally, you would have like one GPU per domain that you want to render for interactive visualization. Thank you.
Anders, nice work. I am curious on the issue of changing the opacity. Does that mean that the transfer function that you're using when you're visualizing is built into training? If when I want to tweak my transfer function, I've got to spend 6 to 12 minutes. Is that right, or do I understand that well?
Yes, so you do understand that well. In sort of the normal 3D Gaussian splatting representation, each Gaussian does learn sort of a baked-in color and opacity, etc. And I don't mention it beyond just here at the end saying we have this other work called volume encoding Gaussians where we actually do explore exactly that. So instead of embedding color, opacity, etc., you just embed the volume value, and then at render time, you just apply a transfer function directly to these volume values per Gaussian, and it ends up working quite well. So in an ideal world, all of these technologies would be combined to give sort of like this ideal scientific workflow.
I also have a question that goes in the same direction. What if you have a transfer function that is not sparse? Like if you have a transfer function where the regions that it extracts are more like homogeneous, does it also work well? Or?
I would say yes. So that's sort of related to this question of depending on how opaque your ground truth images are will sort of affect how well the internal structures are learned. And if it's opaque, or I'm sorry, could you repeat your question? If you have multiple transfer functions, is that right? So there is another work, I believe it came out maybe at the end of last year or earlier this year, where they are training a bunch of these 3D Gaussian splat models at different transfer functions, and then they compose them all into one thing. And it turns out that if you instead use this volume encoding Gaussian representation to learn these things, it's much more resilient to, I guess, unseen transfer functions or unseen opacity maps.
I just wonder if you have if your Gaussians are clumped somewhere around structures that are surface-ish. I suppose this works quite well, but if these structures are more spread out, so you have to have regions that you have to devote a whole lot of Gaussians, would that break the?
Yeah, so that's a good question. Maybe we could just conceptually think of if we were to split this chameleon 128 ways, you're going to have sections that are effectively empty space. So you have to consider how are you doing this partitioning such that you're not having any single domain with a lot of useless or empty data.
Thank you. Are there more questions? This doesn't seem to be the case, so let's thank Andres again. And our final paper in the session will be real-time 3D visualization of radiance fields on light field displays. The authors are Yongyan Kim, Cheng Sun, Michael Stengel, Matthew Chen, Andrew Russell, Yahun Yang, Will Brefwell, David Lübke, and Shalini De Mello. And the presenter will be Michael. Take it away.
Yeah, thank you very much. All right. Hello, everyone. My name is Michael Stengel. I'm giving this talk as my colleague, Jonghyun Kim, unfortunately wasn't able to make it to the conference. So maybe a few words on my background and the team I'm working with. I'm with NVIDIA Research. Starting in 2017, I did research in XR, specifically real-time gaze tracking in the NXP team directed by David Lübke. 2019 on, I worked on real-time rendering, specifically ray tracing and global illumination, such as DDGI, cloud-based rendering, those kind of things. And since 2023, I worked on AI-mediated telepresence and volumetric capture and rendering. And recently, our team shifted towards human-robot interaction. So I'm working in the AMRI team, guided by and led by Shalini De Mello. So a few questions up front. So I see a bunch of you working on radiance fields such as 3D Gaussian. So I wonder how many people in the room have been playing around with that? All right, quite a few. That's cool. So what about light field displays? Anybody using light field displays? Oh, much less, but a few. All right. Okay, this talk is specifically about the combination of both, and everybody else can relax for the next 20 minutes or so. So a short throwback to 2023, our team was working on a solution for real-time avatars for 3D video conferencing. And the idea was to convert from 2D to 3D in real time using a novel and fast generative network. Some special encoding and conditioning was necessary for doing that. But we used an ordinary single webcam as input, which made it very interesting. And we did show this live at SIGGRAPH eTech at the time to hundreds of people. But what made the 3D video conferencing very interesting and immersive was the fact that we used light field displays for presentation. And these allowed the users to see and experience the remote people glasses free with depth, and it felt very natural. And it's also interesting to know that the underlying 3D representation at the time for the face was a neural radiance field encoding as triplanes. Rendering from a triplane follows the basic volumetric rendering principle we heard before. So basically ray marching at each step, the ray march, we look up the set of features from the triplanes and then decode into RGB and density using a small MLP and a shader. However, there was a limitation, significant limitation with triplanes. So we had to train the network at a fixed size, and driving the size higher to include a full body at high resolution was difficult. So regardless, we went with it for a while and made rendering really fast enough to drive a light field display, as you can see here. So those are some later stages of the demo. And the face could be captured, lifted, and rendered in real time, even on a consumer laptop. But now you might expect what happened next. Well, yes, 3D Gaussian displaying was published in 2023, made a big splash. The image quality was really high. The method utilizes the GPU really well. But most importantly for our case was the extrinsic nature. So allocated detail is adjustable and the scene to some extent editable. So we went with that, and a group of colleagues created an avatar generation animation system using splats called Gaia, which is very fast and high quality, better than what we had before. And it's also a nice feature that it was fully compatible to blend shape-based avatars driving the animation. So we started to explore the different flavors of 3D Gaussian splats and realized that detailed scenes without special compression can be quite wasteful in storage. So scenes can be hundreds of megabytes, even higher, which is a problem for streaming Gaussian scenes. And in our use case, we want to stream. So this is specifically true when you try to capture dynamic scenes for free viewpoint video. Capturing dynamic scenes from many cameras is significantly more challenging and creates massive, maybe not as massive as we just heard before, but big data, big amounts of data. So processing these for training frame by frame can really take hours for a single frame. But when you do that, the results can be truly amazing. So here we process some multi-view data from our partners at Clear Angle Studios. And training took a long time, though, when performing frame sequential training. And the resulting scenes were quite large. So as a solution for that, we proposed Queen in 2024, a framework that allows training of dynamic 3D Gaussian scenes in a streaming fashion. The method builds on a learned codebook for attribute-specific quantization and motion tracking. So as a result, the method automatically balances compression based on the scene motion. So the method not just cuts down the scene in size, but also reduces training time significantly, as you can see here in this comparison. So with the streaming and compression in place, we're able to capture and distribute scenes now at very high quality. So it was time for another demo. But we realized, with the vanilla 3D.js tiled renderer, we're not able to render scenes at the performance that we needed, especially now in combination with a light field display, where potentially hundreds of views need to be rendered simultaneously. And 8K or 60K panels are quite common. So I did various optimizations based on the original 3D.js renderer using the graphics API, but still, even on a current high-end gaming GPU, like a 1590, a scene with 5 million Gaussians can't be rendered natively in real time on such a light field display. So the problem is that 3D Gaussians can get very, very small in a highly complex scene, which is really bad for rasterization. Also, since 3D Gaussians are an evolving field with many flavors, we wanted to maintain compatibility with those ongoing research. So we didn't really want to invent a restrictive custom format. So the challenge at this point was, how can we render any streamed radiance field from any novel camera and for any number of views efficiently? So to answer that question, it required us to think from first principles of how light field displays work, specifically the ray distribution introduced by the microlens array of the light field. The reconstructed light rays can provide binocular disparity and motion parallax, but only within a certain viewing angle and at a viewing zone at a certain viewing distance. So the first insight was that we only need to create information where necessary. By the specific display layout. In case of this light field display, this is a horizontal parallax display. The second insight is that neighboring views are typically only slightly shifted viewpoints, so there's a large amount of overhead, so quite similar and therefore redundant information. Still, rendering even a subset of those views can be tricky in terms of performance. So could we maybe cache the pixels corresponding to individual rays and reuse them across views? The problem here is that each light field display is individually calibrated due to the microlens lamination process, which introduces catastrophic inaccuracies without considering that calibration. So each subpixel requires a slightly different ray direction, even on a subpixel, which lowers the benefit from pre-computing pixel-aligned ray distributions. Previous approaches already focused on pre-computing the ray to subpixel mapping and therefore reducing the number of ray marches. There are still limitations with the idea. So it's not well suited for rasterization, but only for ray tracing. Well, that might be okay, but it's still too slow for high resolution 8K or 16K panels. So at this point, tracing splats is still even more expensive on current hardware compared to rasterization. For most scenes at least. But there is a surge, and we heard about it before, in RT-based methods such as 3D GUT or G-Ray from this year, So we're also specifically thinking about unifying the method for light field displays to be compatible with both rasterization and ray tracing. So for our solution, we got inspired by multi-plane imaging and layered mesh representations for constrained novel view synthesis. We show here results from a previous method by Broxton et al. From Google Deep View. So those layered meshes are used for novel view synthesis, and they're quite a heavy optimization to be created. So this is far from real time. However, the quality of the novel views was really high. So for us, we were thinking, okay, this is an interesting and promising avenue. To address the challenges I talked about, we propose real-time 3D visualization of radiance fields on light field displays. Our method takes an already reconstructed radiance field as input and employs a plane sweeping algorithm for efficient multi-view rendering. The method largely avoids redundant ray sampling across views to achieve up to 20x speedups for light field displays. So creating multiple viewpoints involves placing perspective cameras in parallel at the designated viewing distance. Only a single reference camera is rendered through Gaussian splatting in our approach to create an optimized set of multiplane images that can be then efficiently resampled. After rendering all the views, the base image is interleaved for the rendered, for the final display. These animations here show the steps in greater detail. The conventional method would just calculate each view in series. Our strategy is to reduce computation by approximating the volume visible in the 3D display by a series of forward-sweeping planes or multiplane images. Each plane is representing a disjoint frustum of the original volume. Instead of traversing now through the original 3D representation, we composite the sweeping planes into quilt views via an operation we call swizzle blending. A single pixel lookup then on the planes corresponds to the rendering result of a ray segment from the original radiance field, where the latter is much more expensive to compute. This cuts down render time significantly as long as the sweeping planes can be rendered efficiently. So here's now a quantitative result in compute mode in our implementation using CUDA and Python. So we have different knobs, like the number of chunks and the chunk resolution, so we can adjust the compute memory directly. Compared to the baseline method, our algorithm is always faster in all cases. We tested Gaussian splatting, we call this then G2LF, sparse voxels, V2LF, and also NERF, N2LF. And with G2LF and sparse voxels, we're able to mostly preserve the image quality of the sequential rendering, the native rendering, as the MPIs capture the information well. With NERVs, though, the results are subpar without a strategy for better importance sampling, as multiplane images are created at distances that may not be ideal. A solution could be a trained oracle, as we were able to show in previous work in LP3D or live portrait. Here are some of the ablation study results. There are more results in the paper, though. So increasing the number of chunks improves PSNR, but the frame rate decreases. With a higher sampling rate, the resolution of each plane, the PSNR of views increase at the reduced render speed. The number of MPIs and resolution are basically limited by GPU memory. However, the relative speedup over individual view rendering increases with the number of views in the quilt. So you could say, the more you render, the more you save. I think I heard that before. We also tested view-dependent lighting across views by saving spherical harmonics in the MPIs. Although this can significantly improve the quality of off-center views in practice, the improvements are much less noticeable, as multiple views are being integrated from the location of the observer. So storing and sampling spherical harmonics data creates significantly higher amounts of memory. In our pipeline, we reuse the main view's MPI data unfiltered. Please also note that the camera change or dynamic content still results in view-dependent effects, since we carry the spherical harmonics for the source view that we sample from. So besides the compute mode pipeline, we also created a pipeline running in graphics mode in GL and Vulkan. Turned out to be most efficient to render the MPIs in sequence for rasterization if primitives cover sufficient area. We sort the Gaussians once and assign Gaussians to individual slices based on the distribution. We use RGB 8-bit buffers, which turn out to work just fine. As you can see, MPIs are typically very sparse, so this image is mostly black, for Gaussian reconstruction of natural scenes at least. different for volumetric datasets, but maybe that's an avenue for optimization. Importantly, the MPI generation is compatible to rasterization and ray tracing. So from the MPI atlas, we can now resample new views into the quilt view very, very quickly. Per quilt view, quilt buffer pixel, the cost is only a single ray march through the MPI atlas and not the original radiance field. The quilt buffer is rendered in a single pass here. Also, linear texture sampling is basically free and does increase the quilt buffer quality significantly. Finally, we interlace the quilt buffer into the display buffer of the light field display using the display-specific calibration parameters. A few words on the placement of the MPIs. In our CUDA implementation, we processed all Gaussians to optimize the MPI's distances based on the Gaussian distances quantiles. However, since Gaussians are being sorted for rendering anyways, we can just look up the positions of individual Gaussians based on adjustable distances. And it kind of creates a distance distribution function. It's an additional knob that we can now tweak to adjust the reconstruction quality. So we can set higher quality close to the camera where it matters. Information further away has typically less parallax and therefore leads to lower visual error, even when it's approximated by a smaller number of slices. So here's some numbers for the method in graphics mode now that we call G12F-GL. So for a smaller number of slices, the pipeline scales significantly better than our CUDA version, and of course traditional light field rendering. For a high quality reconstruction, we recommend something like 64 to 128 slices. For some scenes, though, you can get away with even less. The MPI resolution should be chosen with respect to the display panel resolution. If chosen too low, quality is left on the table. In our test, G12F-GL is roughly 4 times faster than our Python CUDA implementation and anywhere between 10x and 20x faster than vanilla 3D.js. And here you can now see a demo of our algorithm. The scenes from the MIPMERV dataset, very famous by now, and consists about, in our training, 2.5 million primitives. So this is running on a 5090 for a 16-inch looking glass display that has a 4K panel, and we render 45 individual views. The view number would be higher with a larger panel that has 16K. In graphics mode, our G12F render achieves 250 FPS, and the non-G12F render achieves only 10 FPS. So we see a boost here of 25x. So where does it fail? Well, if you choose the number of slices too low, you may end up with a stack of card artifact, especially in the off-center view. Then, since we resample with the main view, the quilt views are slightly more blurry. Increasing the slice resolution helps, but rendering could get expensive again, and more memory is being used. Also, if you have multiple Gaussian entities, we need to aggregate the Gaussians up front or render individual MPI buffers, but the placement of the MPI planes then might not be necessarily ideal. So far, we have seen static scenes, but we also combine G12F with dynamic scenes from Queen. We call this pipeline then Play 4D. In this case, the Gaussians are streamed to and decoded on the GPU. Also, any other existing 3D.js decoding method would probably work here. I think we'll learn in the poster session about a hardware accelerated method for Gaussian compression, so that will be interesting as well. So here we show some dynamic content reconstructed with Queen and rendered with G12F. The original multi-view camera content is from our partners Clearinga Studios and Infinite Realities. So there are several follow-up directions for the project. First, a trained importance sampler could create much better MPR intervals coupled with implicit radiance fields like nerves. We're thinking also about coupling the method with circles, which would potentially increase the reconstruction quality for off-center views to reduce this stack of artifacts there. Then spatial temporal upsampling could potentially recover detail without rendering at higher resolution. In addition, there are applications beyond light fields, specifically multi-view or multi-camera rendering for robotics and automotive. We want to explore usage for the frameworks like NVIDIA Isaac Sim or NVIDIA Cosmos for automotive. In both cases, there are, though, additional challenges, such as a wider baseline or scene variation and augmentation for reinforcement learning. To conclude, I have presented a method for efficient radiance field rendering for light field displays. The method exploits redundancy across neighboring views. The method is unified and can be applied to any explicit format of radiance fields, and it works with ray tracing, rasterization, and it supports streaming. The method typically achieves speedups of 10x to 20x over vanilla 3D.js, but the speed can be significantly higher if you increase the number of views for light field displays. If you're interested, come see me during the coffee break and check out the demo. I brought a little light field display, or try out the code yourself. It is available now using this QR code on GitHub. And I also want to thank my colleagues contributing to the project. And with this, I say thank you, and I'm happy to take questions.
Very impressive work, Michael. Are there questions?
Thanks for that talk. I noticed you had a VR headset in one of the images on the slides. Have you tried this technique in VR, or is it just for light field displays?
So we did try this in VR. The speedups is just not as significant, and VR, because all the pixels basically go into your eyes directly, you have perfect 3D separation. You want to get highest quality for both views, and typically for 3 Gaussians you can't afford rendering 2 views at high resolution. So it is possible to use the technique, it's just not as advantageous and maybe necessary, since, yeah, I mean, rendering is quite fast enough for VR at this point already.
We have another question over here.
If I understand correctly, an assumption you have baked into this is that all of the cameras are along the same line. Briefly, do you imagine that this could be generalized to the cameras placed on an arbitrary curve?
So yes, right now we have this assumption. I think you could use and try the curve, placing the cameras slightly out of that image plane, and maybe accept slide artifacts. But I think the better way would be to explore the idea that I mentioned, to add depth or surfals to the representation that would allow you to do a wider baseline and more free adjustment of the novel views.
Great talk. So the stack of cards effect that you showed earlier was like an offset from these layers. Is that a property of the way that the light field display, you have to like calibrate for the light field display, or is it something you just adjust freely? Like if you increase this to be something that doesn't sync up with the light field display like separation, would that cause any other visual artifacts?
So the stack of card effect that you see here on the bench is really that you're basically trying to assemble an information that is undersampled. It's kind of just aliasing. And if you place more slices doing that, for that information, then you can reconstruct it better. But it is not an inherent artifact that has to do with light field space. It's really an artifact that has to do with undersampling. And so there are different knobs in this algorithm that can alleviate that, but the better way would probably be, and also I have to say that in practice you can't really see those off-center views anyways, because at some point there is still an angular fade basically with almost every light field display. So I'm showing the extreme example. You can see it later in the demo. In practice you don't see it as much.
Are there more questions? If this is not the case, then let's thank Michael and all the speakers one more time. And I'm holding over the mic to Mike.
Yeah. And I'd just like to remind everyone that the poster session is overlapping with this coffee break, so if you haven't checked out the posters, now's the time to do it. Okay, thank you.
try first?
Yes, yes. I think I'm the first to go.
Okay. Yes. So let's see. I mean, we can see that on the technical difficulty shows that we have USB-C. That may be tricky. Let's see. Do you have HDMI as well?
No, it only doesn't have HDMI.
Okay, so let's see whether.
Well, this is USB-C, so it would definitely not work, I guess.
Yeah, but then we can see if we can find the AV
Oh,
guy.
thanks. Oh, this HDMI, but I don't have HDMI port. Thanks for sharing the slides. Oh, sorry. Yeah, because that's all you have tons of material. Oh. How you doing? Hi, good. How are you? So this is the little dongle that you can use, your USB-C, right? Oh yes. Okay. Oh, okay. And it should pop up right here if it's working. Do you have another dongle? Yeah, you can. It looks like
That's something.
that's gonna pop up here if it's good.
Okay.
You need another dongle. Looks like it. Let me try to see if I get another dongle if that works.
Probably not.
Probably not.
But then I think as he says, you might have it. Is it on? Okay. Hey guys, just want to say in order to keep with the schedule, we should start our second session of our 3D. We got two interesting talks lined up. One about accelerating real-time neural rendering on Qualcomm GPUs, and another one on RDNA architecture. So our first speaker is Xifeng. And Xifeng is a staff research engineer in the graphics research team at Qualcomm, and he works on at the intersection of GPU architecture, ray tracing, and neural rendering. Okay, take us away, please.
Okay, good morning, everyone. My name is Zifeng Li, and I'm a staff graphic research engineer working at Qualcomm. And for this session, I'm going to talk about how to optimizing fully fused MLPs on Adreno GPUs. So first of all, I do want to acknowledge all the teams that has been working on our Adreno GPUs. Without them, this presentation won't be possible. So sincere thanks to all the teams involved. First of all, I do want to introduce today's material with this piece of comics. I think we all agree that we are all living in the era of AI right now, and it seems people are more enthusiastic about putting big AI workloads and such as LLMs on GPUs and start to forget that G in GPU stands for graphics. I hope this is HPG, so some people can relate to this feeling. I do admit that we have tools such as AI-based super resolution and AI-based denoising and try to sprinkle a little bit AI on traditional graphic pipelines, but the problem remains as can we do a little bit more to marry AI and graphics, just a little bit deeper? So that is really the inspiration behind this talk, right? And as for today's agenda, I'm going to first talk about how the multi-layer perceptron MLPs are used in the graphics nowadays, and a summary about the graphics MLP workload, and diving into the implementation a little bit, talking about how to implement MLPs in Vulkan using the cooperative matrix extension, and the fusing strategies, about how to fuse your MLP layers, and introduce our own Qualcomm private extension called cooperative matrix conversion. And in the end, we're going to show some experiment numbers and final takeaways. So hopefully, people are familiar what an MLP is. So this slide is to bring everyone on the same page and to centralize the notations that I'm going to use throughout the deck. So from the beginning, right, for each input samples for an MLP, you have this input feature vectors, and following that, you have this multiple layers of hidden layers. For each hidden layers, you have this vector matrix multiply. The weight matrices is the weight is represented as a weight matrices, and after the vector matrix multiply, you added a constant bias and apply activation functions on them to calculate the next layer's hidden states vectors, which will be used as the input for next layer's inputs. So hopefully people are familiar with the concept. So over the past years, there has been many research focusing on how to incorporate MLPs into your graphic pipelines. Very significant milestones start from Neural Radiance Cache in 2021. This is also where the fully fused MLP is also established. NRC introduces MLP as in the path tracing pipeline. It online trains MLP using a very small subset of the rays that has a longer ray path. And for the rest of the majority of the pixels, you just shoot shorter arrays and resort to that MLP to predict colors. And the similar scheme is adopted in Neural Visibility Cache. But in this one, instead of predicting the actual ray colors, you predict the light visibility. And this can be combined with a Richter algorithm for the better light sampling before the ray tracing pipeline. A slightly different direction, you have this neural texture compression in 2023, right? And for this one, you use MLP to compress your texture offline to achieve very huge compression ratio. And in the rendering time, you just resort to inferencing that MLPs instead of sampling your texture. And sorry. Okay. So building on top of neural texture compression, you have this real-time neural appearance model that instead of you train MLP per texture, you offline train a universal decoder. And for each neural material, it also comes with latent feature textures, which is also trained offline. And in real-time rendering, you have this latent feature texture and a universal decoder pair, so that for each neural material, you can predict a more accurate and realistic BRDF and albedo. And the next thing is mobile nerf. This is while nerf is still a thing. Right now, everything is Gaussian splat. But back then, the mobile nerf is represented a technique for targeting very low-power devices. So for this one, instead of training a very large 3D MLP, very large MLP to represent your 3D scene, you train a triangle soup kind of a model, but coupled with a latent feature texture. And while you're rendering such a model and in the fragment shader, you actually resort to a very small MLP that trying to decode that latent feature texture into our final color. And for this one, we actually contribute the Vulkan samples back to the official Chronos Vulkan sample repository. And this one, we showed how you can implement efficiently a fully fused MLP in your fragment shader. And here's a QR code, so if people are interested, you can take a look. And very recently, you have this real-time rendering with a neural irradiance volume. This only comes up in several months ago, right? This is to solve the diffuse global illumination problem, right? Traditionally, you would use a probe-like method to bake the diffuse color of your static scene. For this one, you actually train MLP offline. Extra perks it adds is the MLP can actually learn about time, right? So imagine if you have a static scene, the light changing from the morning to the evening, right? The MLP can also learn from that. And in the rendering, you just resort to the MLP to basically sample the diffuse color of your static scene. So if you generalize how the MLP is used in graphics, right, what you observed is that if you think about the life of a pixel, it can go through many, many shader stages. You have your traditional VSFS pipeline, you have your ray tracing pipelines, and you can go through many compute shaders. The MLPs can be used to substitute some hard-to-compute shader math. Basically your input vectors can be anything ranging from reheat point coordinations, right, directions or latent feature textures, and your output can be anything ranging from RGBA or BRDF or even light visibility. Among all these use cases and research examples, there are some shared characteristics regarding the MLP network configurations, right? Because we are targeting real time here, the MLP used in here are usually pretty small networks in two senses, really. One is that the hidden neurons are pretty small. It's ranging typically from 16 to 64, right? In some use cases, you do see 128s, but that's pretty rare. And the other thing is they are pretty shallow networks. Typically, choices are 2 to 5, right? Of course, those numbers can be adjustable based on your targeted quality. And the other thing is the weight matrices are pretty much shared within a certain scope. For neural radiance cache and neural visibility cache, they are shared per frame. And because it's online trained, right, after the weight matrix is updated, you have a new set of weight, but across a frame, the weight stays as the same. And for neural texture compression, the weight is obviously stays the same if you are inferencing pixels for within a specific texture. And all these properties that actually makes fusing the MLPs realistic. And the other thing I want to talk about is inferencing versus training, right? Our observation is that training is generally less costly. This is, of course, performance-wise, because from all those examples, the training is either done offline, which means you don't have to worry about it during rendering, or even if you're doing online training like an RC or an VC, it's typically trained with a small subset of the samples, usually a few percent, right? And what you really need to worry about is the millions of the inferences that you cannot get away during real-time rendering. So let's talk about implementations a little bit, right? Given all these shared characteristics, how should we implement MLPs in the context of Vulkan? There are three major ways now the programmer can be used to implement MLPs. The most straightforward way will be just use your shader intrinsics, right? Just use your vector ALU and implement that in any shader stages. Our previous samples of the mobile nerf actually uses this way. So there are some tricks you can do, but that's not the main topic for today. The main topic is cooperative matrix, right? The ALU method is easily bound by your vector ALU throughput. To solve that problem, Kronos does publish this cooperative matrix extension, which exposed software or hardware matrix acceleration by vendor. So it is a subgroup level operations, but it's targeted as matrix multiply tools. So you have to kind of reposition your MLPs, which is a vector matrix multiply problem, into a matrix multiply problem. The other way is cooperative vectors. Some vendor does support this. The best thing is that the input and the intermediates kind of stays as feature vectors. It is also works in any shader stages and also exposed to matrix accelerations. Supporting cooperative vectors are actually in our roadmap, but it's in the future. For now, on Adreno GPUs, we do support and recommend using cooperative matrix to implement fully fused MLPs. As I mentioned before, right, MLP in graphics is intrinsically a vector matrix multiply problem. So the first step is to assemble your per pixel feature vectors into a matrix. To do that, there are several ways. You can use a dedicated shader passes to basically assemble your feature vectors into a matrix, and in the next shader, you use your cooperative matrix extension, and you also use our own private extension, which I will introduce later, to do this step more easily. After we convert it into a matrix multiply problem, we can use the cooperative matrix API, which provides these opaque matrix handles and the corresponding loading functions and matrix multiply add functions, right? The API are designed in this way to be opaque because the vendor can have their specific optimizations such as layout transitions and data movement, right? But the problem is by having these opaque handles, it also imposes certain limitations to the programmer, which I will talk about later. For explicit cooperative matrix optimizations on Adreno, we do have a great talk by our colleague Amir on Vulkanize 2026. So here's a QR code. If you scan that, you can get more information. And that's just for one layers, right? So to implement multiple layers, and naive implementation will be you have a dedicated dispatch for each layer, right? And that imposes this very heavy round trip to global memory for your intermediates, because you have to store your intermediates back to global memory and read it back for your next dispatch. This is obviously inefficient, right? And you also suffer from this multiple dispatch overhead. And instead, what we really want is fully fused MLP, which means all the layers and the implementations are implemented in one shader and a single dispatch. The problem is that in this way, right, you have to think about how do you store your intermediates so that it can be preserved somewhere on your chip, that it can be fully resolved by your previous layer, but also accessible for your next layer. If you think about on your GPU, what the programmer can have, the programmer only have a few places that they can have control to actually store your data. You still have your global memory, right? You have your shared memory, and you have your private memory, which usually is implemented as a general purpose register. And in the API, in the cooperative matrix API perspective, that really translate into how to use these different scopes to back up your cooperative matrix opaque handles for your intermediates. So then how do you, so that is really what the fusing strategy is really talk about, is how do you implement these fusing strategies using these different scopes, right? For global fusion, the API does support it naturally, right? Whenever you have done with a particular layer, you just do a cooperative matrix store back to global memory, right? And then for the next layer, you read it back from global. But for global memory, it does support a very large size, but the bandwidth is kind of limited. And for shared fusion, the cooperative matrix API does support to have a shared pointer in your cooperative matrix store, right? But for shared memory, it does provide a better bandwidth, but the size is kind of limited. It only works in a particular work group. And if you are storing your weights also in your shared memory, then you have to think about the occupancy issue if you allocate your shared memory too much. And for GPR fusion or private fusion, that's an interesting story because that's obviously the fastest chip area that you can access. But the problem is that the programmer usually don't have the full control on how the registers are allocated. And that is probably the reason why the standard cooperative matrix API don't have explicit kind of definition on how to preserve your matrix multiplication results in the register. So that is what we're going to talk about today. So can you really fuse in the GPRs? The problems really comes with the API restrictions, right? So the intermediates must perform a round trip to memory, either global or shared, so that it can be used as an input matrix for your next layer. This is by design, right? So to solve this, we do publish this cooperative matrix conversion extension. It provides with these two APIs. One is called CoopMap to vector, and one is called vector to CoopMap. So the purpose of these two APIs is to break the subgroup level opaque handles and return a private array so that we can return the controls of these opaque handles back to the programmer. In the context of MLP layer fusing, by using these two APIs, the programmer can have explicitly control of how the intermediates is stored. In this case, is in GPRs. There are more capabilities with this API, right? As I mentioned before, right? For repositioning the MLP as a matrix multiply problem, you need to assemble your input vectors into a matrix, and this extension can also help with that. It also has APIs for very efficient bit casting and element access. Here is a QR code for this, our own private extension. If you're interested, please scan. Has more information about that. Now let's talk about performance a little bit. We tested different fusing strategies using the neural radiance cache as an use case. It has, just following the original paper, it has 3 hidden layers and 1 output layers for the RGBA value. It has 3.7 pixel inferences, so 1440p, right? We tested on our latest Snapdragon X2 Elite Extreme platform. You can see that we have different testing scenarios. We use the unfused MLP as a baseline. We test global fusion, shared memory fusion, and private GPR fusion. On the very right-hand side, we have this theoretical max to provide a kind of a ceiling of each of the use cases. The theoretical max is calculated based on the maximum teraflops the hardware can support. So no latency, this is the speed of light, right? So if you look at the numbers, it's obviously, you can see that you should always fuse your networks when possible, right? Because it's easily 2 or 3x compared with unfused MLP. And the other thing is that larger networks does give higher efficiencies in general because we do optimize specifically for 64 matrix, but on the other hand, using a 64-byte network is intrinsically expensive. And the other thing is, if you compare about global and shared and private or GPR fusion, you can see that you should choose your fusion strategies based on your network configurations, right? And it seems like shared fusion always outperform global fusions in general, but we do see use cases that when you allocate too much shared memory, the occupancy issue goes down, especially when your weights and intermediates all allocated in shared memory, and that is the place where you should look out, and maybe try global as well, so that you don't waste your performance. And then for GPR fusion, you can see for 16 wide, right, it does provide the best performance, even for 2x compared with shared memory. But for 32 and the 64, we do see that currently using GPR fusion with extension does create a very high limit limit our compiler to allocate enough registers. So this is still in work in progress, and we will upload our latest updates after this. And for all these tests, we do have our sample code available in our Snapdragon Studio repository. So if you scan that, it has more use cases. It has NRC use cases and also have neural texture compression use cases. So please try that out if you are interested. So for the final summary, right? So we show that MLP can be used to replace complex shader math, right? And it is becoming a popular per pixel graphics workloads. It does require per pixel vector matrix multiplication, which can use the cooperative matrix extension to solve it. To get better performance, you should always fuse your MLPs, and because the bottleneck is not just math, it is moving the intermediate vectors between the layers. And we compare with 3 fusion strategies, right? You have your global memory, shared memory, and private, and we introduce our Qualcomm extension, which you can convert this vector to cooperative matrix opaque handles so that you can enable your GPR fusion and also support more efficient vector matrix operations. And the final advice is you should choose your fusion strategy based on your specific workload and network size, right? For large workload, definitely try out fusing through shared memory first, but do look out for occupancy issue. For smaller network, you can choose fusing through private by our extension. And that's it. Thank you.
All right. Are there any questions?
Hi. That was a really good presentation. I was wondering for the timing results you showed, what data type were the MADMOs? Was it 32-bit floats?
Yeah, they're all in half. Floats,
half.
Yeah, float 16s.
Okay, cool.
Yes.
Thank you.
Thanks for the talk. Are these extensions available on older GPUs? Or how far back does support go?
Currently, this is supported on our latest laptop tier and mobile tier. For backward compatibility, I'm not so sure. I have to check on that. But this is really a recent published extension, so yeah, there might be some issues for very old devices. Yeah.
Thanks.
So I think on your 4-layer MLP slide, it still looked like the speed of light that you got. The best was, I think, 75%. Is that like an indication that the math is like 1/3 overbuilt, or are there other extensions that will close that gap and get closer to the speed of light?
Well, yeah, that's a really good question. So this speed of light is purely like mathematical calculation based on the maximum teraflops, right? It doesn't consider any memory latencies or dispatch latencies, right? So if we can get 100%, that will be superb. But for now, the best we can get is for the smaller network is 60 by using the GPR fusion, and for the wider network we can get about 80. But there are some latencies that you just cannot avoid, right? Like dispatch latencies and yeah. So there might be some other rooms, but for fusing, like for the optimization that you can get out of by preserving the intermediates, this is the best we could get. Yeah.
Any more questions, guys? I guess I have a question then. So, as you've mentioned, right, the neural texture compression, well, I mean, what you need is, as you say, is a per texture working set of weights and potentially even a different layout of the MLP. I don't know if that's included, but so how do you deal with like you know, lots of divergent requests?
Yeah, that's a really good question. So that is why I specifically talk about the weight sharing around here. We do not explore into the divergence issue too much, but because we are seeing that even for neural texture compression, per texture you are sharing the weights within the pixels, right? But there are some simple tricks you can do, right? You can sort beforehand so that you can pick out the pixels. If you say you have 16 textures, you have a pre-pass that select your pixels belonging to one texture and assembling them into one subgroup so that they don't have to suffer from the divergence issue. So yeah, you do have to do some pre-processing about that. If like techniques like shader execution reordering can be used on compute, that would be great. But unfortunately, it's not the thing right now.
Thank you.
Hi, thank you for the talk. Speaking to a little bit of back to the vector ALU kind of implementation of these methods, how much of a advantage do you think you could bring to those kind of methods using more like creative register memory use? Like, is there still more space to be made in this for hardware that doesn't support cooperative matrices?
That's also a very good question. So as I mentioned before, and we do have sample code about this, you can achieve pretty efficient vector AL, not using the cooperative matrix extension. You can still achieve very high performance. We do have sample code in both the mobile nerve sample and also actually in our the final QR code we published, right? That repository also have an ALU version of optimizations that we did, and then actually achieve pretty close performance as the cooperative matrix extension. But this is really kind of workload specific and really specific on which shader are you working at, right? And the cooperative matrix extension serves as a facade so that each vendor can have their own optimizations, right? So obviously different vendors will have different optimization opportunities if you're using this cooperative matrix extension. So really no definite answer to that, but if you're specifically looking for optimization techniques you can do for vector ALUs, I would suggest you to look at our code and you will get more information from those. Yeah.
Thank you.
All right. Oh. Yes, interesting approach. So when you're caching this data in the register file, doesn't that increase the register pressure and potentially impact occupancy? Or were you already going to keep it there anyway?
Yes, definitely. If you are fusing through your registers, that definitely increases your pressure, and you can see this that in this performance, right, we can only make it, for now, we kind of show performance with the 16 wide, which has the lowest usage for your intermediates. But for 32 and the 64, we are still working with the compiler team so that we can support this for a larger network. So definitely, that's the downside of using the GPR fusion. Yeah.
Okay, thanks. Okay, guys, I think we don't have time for more questions, so just ask Zifeng offline. So give another round of applause to... All right, so our next speaker is Kunal Tyagi. Kunal is a graphics researcher at AMD, and he works also on the neural rendering and real-time graphics front. Has been a key contributor to machine learning R&D on various FSR technologies. Okay, Kunal, take us away.
Hey everyone, I'm Kunal from AMD. And I focus on hardware-software co-design, mostly around generative AI, neural rendering, and real-time graphic pipelines. RDNA 4 is our latest architecture, and it has been thanks to hundreds of engineers who have poured their hard work into it. So let's see if we can talk a bit more about what it actually is, or why we should even look into the architecture. For some people, it's just nice to nerd out a bit about it. Knowing all the little details is fun. For some people, it's more about figuring out what the hardware tells you in performance counters. And for the majority of people, it's about gaining performance from the hardware. And yeah, I have my priorities reversed. RDNA 4 has a lot of new features, and some of them require a shift in thinking. And you will see that tiny thinking bubble, because it requires a shift in mindset on how you write your shaders, how you think about the workloads. At the same time, RDNA 4 is also a more powerful architecture, and you will see a nice smiley face when you don't need to do much, and your software stack can take care of most of the heavy lifting and give you extra performance. So let's start at the bottom and build up the RDNA 4 GPU. The basic building block, I think everyone knows, is very similar to a CPU core, which we call a lane. And instead of having 1 core or 4 cores, we have 32 of them, and we call that a wave. To hide the memory and execution latencies, the RDNA 4 architecture keeps multiple waves resident. And each one of them lives in a wave slot. The wave slot basically keeps track of everything that you need for a wave. The program counters, which barriers is it subscribed to, what registers does it have, any scratch memory allocation, etc. And there's a long laundry list of items it needs to keep track of. For workloads with unknown latencies, you want to maximize the number of waves so that you can keep at least one wave active at a time. If some wave is waiting for something, at least one wave is there that can make forward progress. On the other hand, if you know your workload very well and you can manage the latencies, you can get around with 1, 2, 4 waves at a time. The lanes are fed by general purpose registers, which we call them VGPRs for vector general purpose registers. There will also be some for scalar later on. This is a hard limit. You cannot ask for more registers than what are physically available on the chip. So usually, register pressure is something that everyone talks about. And RDNA 4 tries to alleviate this by allowing dynamic allocation. And as always with dynamic allocation, you are not sure whether or not you will make forward progress till there's space available in your pool of memory. So as you can see, some of the waves will be blocked till there's some other wave which calls back, basically deallocates the registers and allows the other wave to make forward progress. It's basically just increasing some latency, but at every cycle, some or the other wave is able to make forward progress and increase the performance of the GPU. The biggest benefit is for the shaders who are very complex, doing complex tasks, complex materials which need a lot of VGPRs, or doing matrix multipliers which need a lot of registers as well. Beyond that, we have the scheduler. It's basically the brains of the shader core. every cycle, it picks which instruction from which of the resident waves to execute. It figures out which wave is blocked, which wave is doing some shared execution resource, which will come later on, and it enforces all the rules that you can think of regarding memory accesses. More and more workloads have basically less coherent memory access patterns, and what I mean by that is like different waves want different kind of memory accesses. Some waves might be doing ray tracing, other waves might be doing shading. So you don't want a wave to get stuck behind another wave which has a very slow memory request or which is waiting on a synchronization. So the RDNF4 scheduler has a different FIFO for each single wave. And this allows each wave to make progress independently without waiting on the other wave, which might be slower. This is a great news for compilers and people who want to optimize their application with fewer trial and errors. You don't really want to be stumbling around in the dark. The RDNF4 scheduler essentially allows you to figure out at very fine level what do you want to wait on, how do you want to make forward progress, how do you want to synchronize between waves, and exactly which waves in what way do you want to synchronize. Coordinating waves was never easy. It's never going to be easy, but at least with primitives like named barriers, you have a complete set of primitives to build upon. For commonly used functions, I think people talked about some expensive operations like exponentiation. We have something that we call as transcendental unit. These are fewer in numbers as compared to the 32 lanes that we have, but they're also on a separate path. So running transcendental functions doesn't block the FMA or the ALU for other waves. Alongside all of this sits a scalar unit with its own scalar registers. It handles control flow, address computation, basically everything that you need to be common across all the 32 lanes. And this way you are not spending cycles computing the same thing redundantly 32 times. RDNF4 also improves upon the AI accelerator for matrix multiply and tensor math. All the 32 lanes participate in producing one 16x16 output tile. WMMA is only available on a restricted set of types, but I think it's a long list of types regardless. The throughput jump is vital in accelerating features, for example, FSR upscale. And with a competitive TAA and upscale solution, it lowers the amount of work required per pixel, giving extra headroom for all the spatial expensive shaders that you want to run. The FP8 WMMA in RDNF4 enables a fast and efficient implementation, so you can go quickly from your R&D directly into the implementation without spending a lot of time figuring out how to quantize, how to trade off, etc. WMMA can also be used in a lot of other ways. People have been talking about doing large matrix multiplies or doing small MLPs. And with a 16x16, you sometimes need to tile. Let me see if I can get this running. Yeah. So you can tile in different ways depending on whether you are bottlenecked on your GPRs or you are bottlenecked on your memory. A different way you can do is if you are doing software rasterization for some reason, you can tile those 4x4 multiplies into a 16x16 multiply. Sure, there's a lot of zeros, but because this is separate hardware, you still get performance benefits regardless of that. There are a lot of extensions that try to hide the details of like how you actually do the WMA, and they work fine. However, if you want to extract that last bit of performance, you need to be aware of the exact layout so that the overhead between shifting layouts is not too high. And one of the big benefits of the RDNF4 layout is that with one operation, you can transpose the entire input matrix. This is beneficial because you don't need to go to the scratch memory and come back. So all the 256 elements, they are shifted in just 16 cycles. The higher throughput and better layout enables using MLPs within shaders. Simple MLP with the right configuration can give you faster results or a more coherent execution flow depending on what you are looking for. For example, if you have a 3-layer MLP, it can finish in 384 cycles in the best condition. Some example of places where we see a good return of investment on all the effort to write high performance code and do the R&D are in neural texture compression, in complex materials, in radiance cache, etc. So this is an example of a 1SPP image that, okay, it's just flickering on my end. That's good. If you use some neural radiance cache with better light sampling, you can immediately see a performance improvement. Let me flip back and forth to show that. The NRC implementation essentially approximates the scene lighting, is trained on the fly using a subset of pixels on the screen, and that can be as few as 5% pixels. So you are not incurring a very high cost for the 5% of pixels which need a deeper path length. You can think of it as like a trainable cache similar to Shark. I think Shark is very commonly or decently commonly used. And we can leverage WMF further to denoise and super resolve as well. And it's a bit more efficient to do both of them at the same time rather than do first denoise and then do super resolution. The NSSD solution that we have allows a fast, high quality image, and it at high resolution that closely approximates the full real-time path tracing. In this case, you can see like most of the noise is gone. You can also make out some of the details on the wallpaper to the left. Yeah, to the left. So to recap, this is what we have seen so far, right? It's a lot of small level stuff. Let's collapse them into one block. We can call it SIMD, even though it's no longer SIMD. We can duplicate it and add some ray tracing acceleration as well. To accelerate traversal, RDNF4 doubles throughput, as well as it provides a dedicated ray transform block. This means less work for the shader for all the transformation required by instance nodes and oriented bounding boxes. The oriented bounding box is also new in RDNF4. RDNF4 also enables smaller BVH trees. I think there was a talk on the first day regarding how wide BVH trees are helpful. RDNF4 has a 8 wide BVH node compared to a 4 wide, but it takes the same amount of space, which is 128 bytes. By doubling the number of nodes, you basically squash your BVH down. The fewer layers that you need to traverse, the faster your ray basically traverses the entire scene. Compressing the triangles also results in significant benefits. Basically, most of the benefits comes from compression of triangles because they are the majority of the cost for a BVH in terms of memory. For RT, like I mentioned, RDNF4 provides oriented bounding boxes. This is technically free with AMD's supplied BVH builder, but if you are writing your own BVH builder, you should be aware of some peculiarities that AMD's OBB implementation has. The OBB node basically carries extra 1 byte index. Otherwise, it's the same as an ABB node. The index is used to look into a lookup table and figure out the rotation matrix for that. And there are a bunch of specific rotations which you can look into. So there's coordinate axis, that means rotation only around x or y or z, edge diagonals, that will be x, y, positive x, negative y, etc. And body diagonals, so x, y, z, some combination of positive and negative for all the axes. And for particular angles, 90 degree with coordinate axis is useless. It's not there in the lookup table. But yeah, I'm just showing that to complete the entire diagram. Oh, and all the children are transformed by the same rotation angle. So you cannot have different rotation angle for different children. All the 8 children will be rotated by the same angle. OBBs are really helpful when the geometry is not axis aligned. I think that kind of is obvious. You can see in the image that for this particular crane, the hotspot of the traversal count is really, really reduced compared to the ABB implementation. For artists, this means you don't need to worry too much about how your geometry should look like. You are more free to be creative with your world scene generation. Overall, each of the RT features, they pool together to give roughly 2x improvement and around 20 to 30% memory savings. So RDNF4 effectively allows the next generation of games to be more immersive, full of details, be more dynamic, and this was essentially, this was a bit out of reach on the earlier generations. So is this over? Not yet. We have a lot more abstraction layers to go through because whenever there's a problem, you always add one more layer of abstraction. So the next layer of abstraction about this is called a compute unit. what a compute unit basically is a smallest unit that can run a wave group's worth of waves. What does that mean? So every wave needs to talk with your memory subsystem. That is enabled by the GL0, which is the lowest level of cache available. And all the requests that a wave makes go through either the load store unit or the texture unit. The texture unit does the address computation, sampling, filtering, etc. for the texture fetches. Load store unit is responsible for address generation, figuring out which cache lines you want, because when you're writing code, you are basically doing 32 independent accesses, and to figure out which cache line needs to be loaded for that, that's the job of the load store unit. Then the next level of abstraction is the wave group processor. This consists of 2 compute units along with the scratch memory or local data share, instruction cache, and scalar cache. The local data share is used as a shared memory. You can use it for tile reuse, you can use it for reductions, cross-lane, or cross-wave communication, etc. It's a scratch memory for whatever you want to do. The instruction cache feeds decoded instructions to every wave. Usually we have a repeated shader in the form of like multiple waves. So having a cache for the instruction specifically allows us to lower the latencies for the execution. The scalar constant cache backs the scalar units with uniform constants. Every constant that you declare is stored in the scalar cache. This is a schematic that I'll be using for WGP. It's formed of every block that you saw just unlabeled. So we take this and we stamp it out 4 times into an array and give some cache as some render backend units, and we get a shader array or SA. There's also a GL1 here, which is it's a write collecting cache, and it sits between the GL0, which is per WGP, and the GPU-wide GL2. The render backends do the final color, depth, stencil output, blending, MSAA resolve, etc. And of course, writing to the frame buffer. The render backends consume pixel data exported by the shader cores. So now we have a complete shader engine. This is a self-contained graphics plus compute pipeline slice. This is the order of basically what we stamp out multiple times to create a GPU. So a GPU will have either 1 shader engine, 2 shader engine, maybe 100 shader engines, but it will always have some unit of a shader engine. It usually has 2 shader arrays. It also has a shader process input. SPI is basically the wave launcher. It's the high-level thinking of which wave group has how many VGPRs available, what should be the, like where should the next wave go, etc. There's a primitive assembly. It gathers vertices into primitives. It does clipping, viewport setup, etc. Shader export moves the pixel shader outputs from the shader core to the render backend and handles position parameter export for vertex work. It's the handoff point between all the fixed function pipeline and all the, well, compute pipelines. The scan converter rasterizes primitives into pixel quads and generates coverage for the pixel shaders. This is all pretty traditional, so not a lot of new information, but still putting out there for people who are interested to look into what exists in the architecture. So we are at a stage where we can do the final zoom out into the GPU. We can collapse the entire shader engine into 1 block. A full RDNA4 GPU instantiates multiple of these units, like I said before. They all share the same GL2 cache, which is the coherence point for shader complex and the backstop before the last level cache, which is the MAL, memory attached last level. An efficiency arbitrator manages GL2 MAL traffic, so if you notice EA somewhere in your profile, that's the efficiency arbitrator. Command processor fetches and executes command packets from the kernel mode driver and dispatches compute and graphics work. The geometry engine handles vertex fetch, primitive setup, feeding the primitive assembly in shader engines through SPI. And these together form the work generation front end for the GPU. It's hidden from the users, but from the perspective of the GPU, this is the front end for work generation. MAL sits between GL2 and your system memory. It's basically responsible for reducing the bandwidth by keeping the hot data on the chip itself. And VRAM refers to system memory over here. If you don't have a VRAM because it's an APU, is the same meaning for the chip. RDNA4 has tweaked the GL2 cache to give the best performance across multiple workloads. It has larger capacity. It has a larger cache line to do essentially implicit prefetches, because a lot of the data now has moved into larger textures, larger BVHs, matrices. So without needing to do any prefetch on the application side, we get a performance improvement because of this implicit prefetch. RDNA4 also brings configurable behavior per load at GL2 and GL0 cache, which we call as like near and far cache. So you can decide, oh, I want this cache line to be resident at GL2 but not at GL0, or the inverse depending on your workload. And for example, for hash grid, right? Every time you access a hash grid, you are going to be accessing a different location in your scheduler. But maybe across your entire workload, it's better to keep that hash grid resident at the GL2 level. Or maybe not. You can figure out and choose the best configuration for your application. And congrats, we have a GPU. Which one? 9070 XT. This is a complete GPU. We went from all the way down from a single lane, technically 32 lanes, to SIMD, compute unit, WGP, shader array, shader engine, and then a GPU. RDNA4 also brings better profiling. This enables you to optimize, do targeted optimizations for your workload. How efficient is the delta color compression? Where's the bottleneck in the inference? Are you loading more from PCIe or more from the VRAM? Are all the geometry engine and primitives balanced across the shader engine? You can dig deeper into the data with basically all the same tools, but more insight. So to recap, what does RDNA4 bring? It brings better out-of-the-box performance. Free lunch, especially if you are bottlenecked on a single workload. If you're not bottlenecked on a single workload, it brings a lot of tools for you to use to figure out how to extract the most performance out from the hardware. If you are mixing ray tracing with raster or with ML or any combinations of these three, you can do that with much less headache and with much less impact on the other wave, which was not bottlenecked before. And of course, each of these features has some counters associated, a lot of counters to be honest, and I'm just giving a sneak preview into which ones you should be on the lookout for. RDNA4 gives strong performance on existing workloads independently, as well as mixed workloads like NTC, NRC, interactive, NPCs, etc. In case I skipped over some stuff, this is a glossary of terms that you can use to refer. Maybe I accidentally spoke some abbreviation before explaining what that is. And if you are interested, this is a long list of resources that you can look into and figure out exactly what RDNA4 is all about. Thank you so much. Any questions?
Are there any questions, guys?
Great talk, thanks a lot. For dynamic GPR allocations, do you allow user to somehow tell in the kernel what should be dynamic allocated or not, or versus this is all compiler magic?
There are instructions that allow you to do dynamic allocation. It depends on your software stack whether or not those instructions are available to you as a user, but the instructions are there. LLVM recognizes them, and HIP also recognizes them.
This register magic is really interesting. What keeps there from being deadlock? How come there can't be multiple waves that all want to acquire registers and then no one can get all the registers they need? Is there something that avoids deadlock?
That's the job of SPI. So when you are scheduling a wave, SPI takes care of figuring out whether this particular WGP can take this additional wave. Right, so it has heuristics inside to see that, oh, we should have some headroom available in a WGP before scheduling a new wave onto that WGP. So if there is not enough headroom, it will send it to a different WGP.
So there's some reserved register headroom that
yes,
makes sure
there is some reserved
there's
register
no
headroom.
deadlocks.
I have left some space on the top, the second bar to show that.
Okay, thanks. That's awesome.
Yeah. Otherwise, like, it could be a situation where none of the waves could make forward progress, right?
So with the native support for oriented bounding boxes, do you have a sense of like what differences are you seeing in practice for real world scenes performance wise?
So it's difficult to tease out exactly what's the impact of OBBs on like a specific scene. It changes from scene to scene. If you are looking at older games, it's a much lower impact. On newer games, we see much higher impact. On our internal test, I have given some numbers. For example, if you are counting how many max iterations you need to do per ray, we see a 50% reduction on that. If you are looking at the averages, we see a 20 to 25% reduction in the number of iterations we need to make per ray. So yeah, and 20 to 35% fewer instance node tests.
So when you account for the, assuming they have a higher cost, like what like end result do you see? Like?
In frame rate?
Yeah.
I don't have the numbers now, but I have some, well, some I could say low-level numbers, not end-to-end numbers. End-to-end, overall, like end-to-end, we can only calculate with every single feature that is available in the GPU, right? So that's what we see: 75% to 100% uplift for RT-heavy scenarios if you are bottlenecked on ray tracing, and if you're bottlenecked on, ray processing, then 53% faster ray processing. Again, this is internal scenarios. This is not a particular game or something.
Thank you.
Any more questions, guys? Okay, then let's.
All right. Thank you so much. And a small disclaimer that none of these numbers are real world. They are mostly synthetic. Thank you so much.
Stefan.
Great. Okay, well, I'm Mark Kilgard, presenting Warnock Harnessing GPU Geometry Amplification for Vector Graphics. My co-author is Brian Barron in the back in the baseball cap. So when I talk about GPU geometry amplification, I'm not talking about amazing, cool forest scenes. You saw that. I'm actually talking about the ubiquitous 2D vector graphics that you see all over the place. It's your PDFs, your PowerPoint presentations, your SVG, your web pages, your maps, all of that sort of thing that's actually based on 2D vector graphics and outlines. So the eye on the prize for this research is really new GPU-accelerated algorithms for 2D vector graphics that render from a compact GPU representation. So we just have your outline data on the GPU, and we can render directly from that with the programmable shading pipeline. We do that fast, with high performance, and we want to support all the established features in vector graphics. Vector graphics is a lot more content-driven than games are. We want to support this all through a convenient library with a nice API. We want this also to be cloud ready. So even if your application isn't today a windowed graphics app, you can still get your vector graphics going. So the research towards this prize is really methods that we've developed to harness the theory of polar stroking and now augmented to be polar filling. And that includes the ability to have a pixel space error bound on the path tessellation that's generated. And then on that theory side, there's the implementation, which is mapping this to the geometry amplification features of the GPU. And by that, I specifically mean GPU tessellation and on more modern GPUs, mesh shaders. So paths come in and tessellated geometry for that filled or stroke path comes out. And we're able to bound the error of this. This is all done through an Uber shader strategy, so a core of polar tessellation code makes possible all the different variations for vector graphics rendering filled or stroked. So here's kind of the visualization of this. We're using the HPG logo here. That logo is defined with a bunch of Bezier curves, so it's an outline. And what we want to do is efficiently take this outline and without subdividing it or do anything fancy, effectively put it in a representation that's in a GPU buffer that shaders can then pull out and actually tessellate the full tessellation of the stroked or filled path. So in the case of stroking, we take that path in, we stencil it in the stencil buffer, we cover it, we get the stroke result. Likewise, for filling, we compute the winding number in the stencil buffer, we conservatively cover it, and we get the filled result. So that gives us the complete solution here. Our research contributions are really this polar filling idea. This is taking a 2000 SIGGRAPH paper and generalizing that theory and sharing it with polar stroking. So we got one way we can do both stroking and filling, and then figuring out how to map that to these GPU amplification features. These are broadly supported on both current modern GPUs and older GPUs as well. And the crucial thing, and I'll say it a couple times, from one compact representation in your GPU buffer, you can stencil or fill paths. And we have this error metric to make sure that we do it accurately. This is built into a system. If you read the paper, it's really a systems paper. It describes Warnock, a GPU-accelerated 2D vector graphics library for NVIDIA GPUs. Our methods are packaged for easy use, either from C or C++ or Python. And it's similar to kind of what other vector graphics APIs would be. It's a research thing, so it's not publicly available yet. The object model has path objects and paint objects and pins and surfaces. So if you're familiar with Cairo or Skia, this will be familiar to you there. Why the name? It's really an homage to John Warnock, who systematized vector 2D graphics with his SIGGRAPH 1982 paper. We want to bake paths so that Warnock can render them, and that involves a process of minimal lowering. We don't want to do a lot to your path. We just want to get it in a form that the SMT nature of a GPU can go and tessellate. We want to be oblivious to all the things like stroke width and join style and caps and all that stuff. We just want your outline data on there and be able to tessellate from that. The explicit goals, same representation for filling and stroking. We want it hashable. If you've got a path that might be a string in an SVG file or PostScript or a font, we should be able to come directly from hashing that string to the GPU representation that might already be loaded on the GPU to save a lot of time. We want it to be compact. We want it to be about 1.5 to 2 times larger than the CPU version of this, which we actually do. And that's really important. A lot of other methods are substantially larger than the actual representation. So we need to decompose paths for uniform execution. Paths have this wide variety of different commands: cubic and quadratic Béziers, line segments, conics, arcs. There's joins and caps and implicit closes. But we need to map that to a GPU that has a single instruction, multiple thread execution model in the shader cores. Threads can diverge, but we want it mostly converged to get things working well. So Warnock goes and takes your paths and bakes them into a format that fits well into a 32-thread warp that runs on NVIDIA shaders. So this is for efficient GPU execution. We need similar work chunks. So we need to break the path into what we call a path link or simply link sequence. So the input to path rendering normally is just an array of path commands, things like line to, curve to, arc to, close path, and then the corresponding control point numbers that go along with it. There's alternate ways to specify paths, things like strings or glyphs from a font. I'm going to look at a simple path to sort of say how would we go about baking it. So this is just very pedantic, but it's 2 subpaths. They actually are going to get rendered like this. You can fill it or you can stroke it. Notice the filling has this weird behavior, but that's an artifact of the 2 different subpaths have different windings to them. And we need to model that to render it correctly. All of the path commands have their corresponding control points, and those are ordered. It's important that we get that order right. And those each have XY locations that go with them. But the actual path segments are different. Some of them are cubic Bézier, it could be quadratic Bézier, lines, we could have an implicit close. So we've got this wide variety, it looks like, of different ways to represent different path segments. We put that all together, and that's kind of what your path is. We could form this example path as an SVG string. We can actually go and load it in Warnock. Here's a couple examples of how we would do that and how we would do it with just the explicit path commands. But again, what we're trying to do is get this either filling or stroking out of the GPU by just sending this sleep sequence. So what we do is bake that path into something that lives in video memory in a buffer. And so that buffer contains an array of what we call links. And we'll talk about what a link is. And then the links have indices into an array of control points. And then we also, for filling, need to have an array of anchors for each one of the subpath and any conservative covering geometry that we've got. And then we want to have, for indirect rendering, the state that we would use to launch this, to get it actually rendered and get it on the screen. Ideally, we're going to, with a single 3D API command, like one OpenGL command, be able to launch all the work to fill or stroke, tessellate a path, no matter how complicated it is. Now, this is one of the things of warning is these paths. Our example was really simple. It was just 7 path commands, but you can have paths that have tens of thousands or hundreds of thousands of paths, and we can still launch that with a single OpenGL call, even though there's huge amounts of path coordinates. We just need to get it all baked and put into video memory. So this can result in very intricate artwork. Here's some fancy Adobe Illustrator artwork, and you can see the visualization of all the control points. It gets really, really complicated when an artist goes and makes this kind of content. So let's get back to our example path. It's 7 path commands, and we're going to turn that into 12 path links, an array of 12 path links. So we're going to look at what a link is. A link is a couple different things. One is it's your segments, a cubic or a quadratic or a conic rational Bézier curve. It's things like your caps and your joins. If the subpath isn't closed, we can do an implicit close. So there's 10 of these link types. The other way to look at it is some of these link types get used for both filling and stroking. Some of them, like the joins and caps, only get used for stroking. So when we're filling, we just skip over them. Likewise, there's an implicit close line segment for filling only, and stroking just skips over this. But we have all of these potentially baked into the path so we can do a stroking or filling. So what does what Warnock baking doesn't and does handle? The things we want to be oblivious to, we want to be blind to, are things like the fill rule and stroke width and cap style and join style, what the transform is, whether we're non-scaling or not, and what the tessellation settings are, the quality metrics. None of that has anything to do with what we bake into the path. We do need to do some work to bake dashing, and if there's a wide arc, we need to convert that into conic Bezier segments. But the work that we do to get a path in a state to put in video memory is pretty simple. So let me talk a little bit about caps and joins, because that's interesting. Caps actually in major standards can be assigned different kinds of geometry, round caps, triangular caps, and we need to be able to map that dynamically based on the pin state. And so we actually do that in the tessellator. Likewise for joins, there's different kinds of join geometry that exists, and we map that dynamically along with the dynamic join state to form the correct join. So this all works, and you don't have to worry about caps or joins. It has nothing to do with the baking process. It just happens at rendering time. But there's various types of links, and it appears all quite heterogeneous. What does a cap have to do with a cubic or a quadratic or an implicit close? These all seem like different things, but GPUs thrive on homogeneous data processing. And so the challenge is taking this kind of apparently heterogeneous representation of 2D geometry and mapping it to a homogeneous layout. And then there's the obvious related challenge of, now that we've got it in some homogeneous layout, how do we design a shader that executes in some kind of converged way to efficiently execute on the GPU? Spoiler, yes, you can do this. So let's just think about a triangle. This is pretty obvious. How do we represent a triangle? Well, we have a list of positions, a vertex array, and a triangle is really just 3 indices into that. Kind of obvious, right? Well, let's think about a link the same way. A link, non-obviously, we're going to treat as 6 indices. Up to 4 of these are going to index into positional control points, and up to 2 of these are going to index into gradient control points. So 6 integer numbers are how we encode any given link. Now, we also need to know the link type, but it turns out we can implicitly encode that by reserving index 0 in a clever way. So let's look at how we might do that for our example path and make this 7 path commands into 12 links. So we're going to start out with the first cubic Bezier segment, and you can see across the top is the control point coordinate array. It's all of the different XY numbers, floating point numbers, that our control points go into, and we've got indices that index into that array. 2, 4, 0, 6, 4, 4. That indicates this quadratic Bezier curve. Likewise, we need to encode joins. That has an index array, and the blue 0, 0, 6, 6, 4, 8, and the shader can decode that and draw a join. We can also do a cubic Bezier curve. Again, it's just 6 integers. We can do a line. It looks like a cubic with just repeated indices. And then we can handle things like caps, both the initial and terminal caps. Again, they're all encoded as just 6 integers. And then we can do the implicit close as well. Now we've got enough information in GPU memory to basically have a polar stroking tessellator go and emit the tessellation that we need into the stencil buffer, and then we can just run the shader again, now drawing into the color buffer and resetting the stencil buffer to draw our stroke following the blend once and only once rule. Now we need to talk about how to do path filling. This is the polar filling part. This is new in this paper. We do filling of paths on the GPU generally in a 2-step method of stenciling the winding coverage of the path and then doing a conservative cover of that. So you can see below the kind of triangle fans that we emit with back and front facing triangles that are going to increment and decrement the stencil. They're going to leave the stencil buffer with the outline defined. Now what we need to do is we need to have those anchor points baked into our path. Those are these 3 green points. There's 2 green points for each of the subpaths, And then our conservative cover also has an anchor point. And then we've got the conservative cover that's going to fit over our filled path. So we're going to encode those extra anchor positions into our path buffer. And then we're going to encode an additional set of 6 links to include an octagon that can draw our conservative cover geometry. And so it's just another set of 6 links. And so now in the end, we've got 18 links. Each one of them have 6 indices. And that represents our path in a way that we can both fill it and stroke it along with its anchor geometry. So here's kind of that polar filling in action. And here's the complete example of getting this rendered. So that's the idea. We're going to do this not just for this simple path, but for arbitrary paths. Any glyph, any logo, any map outline, it's all done with the same way. So how do we do this in the shader? How do we get it working? Well, this is the flow chart that describes how we would go render it using either stenciling or filling. What we're going to do first is a stencil step. We're going to iterate over each one of the links, and we're going to fetch the link. We're going to set up the link for polar tessellation, and then we're going to tessellate it into ribs that then either turn into a triangle strip or for stroking, or a triangle fan for filling. And then we're going to do the cover step. For stroking, we're just going to retessellate everything again so we can go and resolve the coverage. For filling, we're going to use that conservative, that octagon that we had, and we're going to emit that instead. Each one of these steps is launched with a single OpenGL command. So how does this actually map to geometry amplification? Well, you can see kind of for each one of these, it's the same shader. So for the vertex, for GPU tessellation, we do fetch the link in a vertex shader. We do set up the link in a tessellation control shader, and we do the tessellation of the ribs into triangle fans or triangle strips in the tessellation evaluation shader. Sometimes we use a geometry shader as well. If we're on a modern GPU that has mesh shaders, we can actually map that to the task shader and the mesh shader. So this doesn't happen where we just iterate on these links one at a time. No, instead this gets mapped to this big, massive parallel hardware machine, and so hundreds of these links can all, and ribs can all be processed at once through this. So here are the 2 geometry amplification pipelines in OpenGL, in Direct3D, and Vulkan, and how they look. Again, in the GPU tessellation approach, we need to fetch the link. We're going to do that on the vertex shader. We've got 6 indices. Those are each going to get transformed, and then they're going to form a patch, and that patch is going to get set up and figure out how much tessellation we need to do. That goes to the tessellation evaluation shader, and the rib evaluation happens there. This is what the vertex shader looks like as a flow chart. This is what the control shader looks like. Importantly, it's executing the math that has the theory in the polar stroking paper. The evaluation shader just does the evaluation math in the polar stroking shader, but it's emitting geometry out. In the case of GPU tessellation, you may be like, hey, wait a minute, GPU tessellation makes a quadrilateral patch. It doesn't make triangle strips and triangle fans, but through a nifty effective hack known as NAN poisoning, we can mark certain vertices with a NAN, and when the rasterizer sees it, it says, I don't know what to do with this, I'm going to discard the triangle. And so we basically stitch out the geometry that we need to actually generate our stroke or our triangle fans for filling. So you can see these different patches here, but they all get formed together to draw our stroke. For mesh shading, we actually optimize the layout of our baked path for 32 thread warps. We actually pack up to 8 links into a single link pack, and then we run a task shader on those up to 8 link packs, and they generate the work that spawns mesh shaders that do the rib evaluation. So the task shader looks something like this in its outline. Again, it's doing math from the polar stroking paper, and then the mesh shader is doing the evaluation work to have that be output. There is a path space error metric. This was a big limitation of polar stroking. It only had a conformal angle-based metric. But now there's a metric that's guaranteed without doing GPU recursion, just iteration, to be able to bound the pixel space error. The details of this are kind of involved, so they're in the paper. It's a bunch of differential geometry and for shade distance logic. We did some benchmarking of this on 40 various scenes against Cairo and Direct 2D and Skia. Just give you the high-level view of the performance. Warnock was faster than Cairo and Skia in every one of these 40 instances. For Direct 2D, it won 35 out of 40 times. And Warnock, though, is slower than NV path rendering just because it's so hyper-efficiently tuned. This is something that we want to work on and understand that NV path rendering did a lot more baking work to make its performance possible. So when you look at mesh shaders versus GPU tessellation, mesh shaders is the more modern feature. It is a bit faster to use mesh shaders. There's extensive benchmarking in the supplemental data. So in conclusion, Warnock is this GPU accelerated 2D vector graphics system that's based on the theory for polar stroking and now polar filling, and supports dynamic tessellation, and it supports the GPU amplification features. If you're interested in 2D vector graphics on a GPU, let's talk, and I'm available for questions.
Thank you for the nice talk.
In the back.
Do we have any questions in the audience?
Hi, I have a question about the polar filling approach. It sounds like it's using like a triangle fan to fill a large area. There's sort of pivot point. When filling, especially with this like stencil and cover type approach, it tends to generate, tends to generate a lot of long and skinny triangles that cover a large filled area that can have or tends to have poor performance characteristics, especially on mobile GPUs, etc. Have you considered different tessellation patterns with
that's actually a really informed, excellent question. You can see in the initial geometry that's formed here, it's a bunch of triangle fans, and yeah, they're long, skinny triangles. Actually, GPUs don't really like long, skinny triangles, so that's a very perceptive question. I'm going to flip to the actual mesh shader that runs, and you'll actually see there's this step here that says optional optimized triangle fan topology, and it does exactly that. It takes this triangle fan and it starts doing flips to be able to form triangles that are either much larger or much smaller, and avoids these. We call this bistellar flips, but that's a very perceptive question to realize that that's a problem. Mesh shaders can do that. It's not something we can easily do in the GPU tessellation domain. It is one of the reasons mesh shaders are faster.
Thank you.
Hi, you said that this was for NVIDIA GPUs, but I didn't hear anything that seemed NVIDIA specific. Did I miss something?
Yeah, the question is it NVIDIA specific? It's written with NVIDIA proprietary extensions throughout for a number of different things. There's extensions like sample override. The mesh shader extension that we have has particular features. And one of the things we support well is something in Direct 3D, it's called target independent raster. In OpenGL, it's called fragment mixed samples, where we can have a different number of color samples, fewer color samples and stencil samples, and we take advantage of that. That's very important to do well for vector graphics. You don't want to render into multi-sampled buffers because it's a lot more memory. So perceptive question right now, I mean, this is research. It's put out and optimized for NVIDIA GPUs, but for good reasons, I would explain.
Any other questions? I have one. So you mentioned the efficiency of the baking step. Do you have any measurements on how this compares to alternatives? Does this help with animated parts or faster rendering of documents?
Yeah, so the benchmarking there actually is in the supplemental material. Extensive, benchmarking results at huge numbers of resolutions on each one of these 40 different pieces of content that you can see and evaluate. And it's also all graphed in the supplemental. you can actually see that if you look at the data, you'll see that a lot of this is actually host-bound, CPU-bound. And this is something that's the main reason that we're not as fast as NV path rendering. NV path rendering has some very hyper-optimized things. We're looking forward to putting some of those same optimizations into Warnock so that the performance would improve. Did I answer the question?
Yes.
Okay, great. Anything else?
Let's thank Mark again.
Okay.
You mentioned the reliance on NVIDIA extensions and also that Warnock is faster than Skia, for example. If a version of Warnock was implemented for like OpenGL or Vulkan without using those NVIDIA extensions, would it still be faster, do you think?
Yeah, I think the question was, would it be faster in Vulkan? I've actually, through the miracle of Claude, managed to port things to Vulkan. At this point, it's not particularly different. Again, a lot of that is it's CPU bound on things, and so that won't make a difference until that's really fixed. Ultimately, the kind of optimizations that like NV path rendering were done at a level that's even lower than what Vulkan sees. So we'll just have to see how well it comes out, but I'm expecting we can do much better in performance. And I'll mention there's a bunch of supplemental documents that come along with the paper, so if you're interested in this topic, please check out the supplemental documents. Yeah.
I had a quick question.
Yeah.
What about anti-aliasing, like coverage versus opacity, the conflation of those? How do you handle that?
That's a great question. This is one of the classic problems with vector graphics is we generally compute the fractional coverage of a pixel. One of the things that we take advantage of in practice are modes where we can actually have 16 stencil samples per pixel and 1 color sample. And the stencil test gets evaluated 16 times and then becomes a fractional value that's an estimate of the coverage. It's one of the reasons we stick with the model of doing stencil then cover, because we get to resolve that coverage correctly. It also explains why we need the sample override extension. It's an NVIDIA extension.
Thank you.
Okay.
That's all the time we have for questions. So let's thank Mark again.
Thank you.
Next, we have high-performance, real-time, implicit strand-based hair rendering via software rationalization by Lukas Lip, Adrian Harabo, Michael Wimmer, and Lukas Bod.
Hello, everyone. So hello. So this is work that happened during my Meta internship, and I'd like to share this now with you. As some of you maybe know, Meta has this interest in creating these virtual worlds so that can connect us all. And one side is this photorealism side with codec avatar or hyperscape, mostly like implicit representations trying to capture very high detailed, high fidelity worlds. And on the other hand, I have the stylized direction with horizon worlds, for instance. And we mostly focus on, our work focuses on this stylized version. And usually you represent yourself with a virtual character, and but this includes the body, this includes clothing, but it also includes hair. And we try to tackle this hair part here. And when we want to render hair, we have to consider very complex geometric structures, a lot of strands that overlap, a lot of aliasing. Also, the light transport is quite complex. As you can see here, we have scattering inside the strand. We also have scattering among multiple strands. There are different styles of hair. You can have an afro-like appearance. You can have straight hairs, you can have them tied to a knot. But it's a very important aspect for relatable characters. And when we want to represent hair, we can either do this implicitly with, for instance, Gaussians, nerves, but we lose a lot of control here, and it's not always great quality. On the other hand, we can represent them explicitly, so every single strand is represented, but this often needs a lot of storage, and authoring can be quite time-consuming. And there were further challenges for this project. So one was that it needs to run on low-powered mobile devices, also on XR devices like the Quest 3, which has it needs to render for 2 eyes, so double the resolution here. And usually these devices have a very limited set of features, compute and bandwidth. For instance, the Quest 3 has quite a low memory bandwidth. And as an example, the lack of mesh shaders is very noticeable here. Usually phones don't have this, the Quest doesn't have this. And mesh shaders are often used for this high primitive rendering kind of things. So what we wanted to build upon was this hair mesh representation that was introduced by Cem Yüksel some time ago. And the gist of it is that strands are implicitly defined by a mesh cage. So everything you need to store is just the vertices of the cage, and the rest is then generated on the fly. You can see this on the top, on the bottom right. And also very cool, the styling is described by a few parameters. So you have styling functions that can then move your strands around and create different styles. Also, animation is very easy, or physics, for instance. You can just deform the cage and the hair moves with it. And I think there's also a real-time live thing at SIGGRAPH about this year. The negative side is that it's a bit hard to make assumptions about the groom. Like if you have a very explicit representation, you know how your strands are, and you can easily build it's easily to build level of detail, for instance, level of details about it, for instance. But here you have the styling function, and this one can perturbate your strands quite a lot, and not even the cage itself is a real limit of this. So a hair mesh structure looks like the following. You have the hair mesh, and then you have a bundle, which represents one of those chain of boxes, and inside are the strands, and between those boxes you have the layers, and you connect the strands through the layers. We will look at this soon. So the pipeline was the following. In the beginning, we had a LOD prepass, so a compute shader that calculates how many strands we want, how many control points we need, and then fills an indirect draw buffer, which is then later on read by a compute-based rasterizer, which then assembles the strands and writes to the different layers. In our case, we have a center sample layer and a conservative layer. I will talk about this later, why we need those. And in the end, there's a reconstruction filter. So it's a strand connection filter, it does strand connection for single sample single sample strands. And there's also a directional blur that removes a bit of the aliasing. And then it also blends into the final, or into the other pipe, into the other image that is used by the pipeline. So how is such a strand assembled? We have this example here with a few layers. And in order to get our base strand, we sample one position at each of these layers. So these are the same random numbers for each layer, and we get these points. And then so every thread loads one of those points, and then these threads can share each individual points with each other, so that we can calculate the tangents for each of those points, because
for one for one control point, the tangent relies on the difference between the previous and the next one, for instance. And then once we have those, we write them into shared memory. This is quite easy because usually we don't have that many layers, but in the end we maybe have a lot of control points, and writing each of those into a shared memory would have been too much. So we try to use a different solution for that. So now each thread computes a bunch of control points from this layer control points, and then we style them. So this is the function which the points are put into, and they get perturbed by the styling functions. And then we get our final positions, our final control points. But we need to compute the tangents again, and we do the same again so that not every thread needs to recompute the same control points and then the stylings of those control points. We do this only once per thread and then share the results with the neighboring threads. And then in the end, we calculate the segments, and those also need the neighboring control point so that it can complete the segment. Once this is done, we use just a normal DDA algorithm to rasterize the segments. And here we decide, like, if the center sample of the pixel lies within the projected radius, we write it into the center layer of our buffer, and if not, it is written to the conservative layer, and usually every segment is written also to the conservative layer. And so for the LOD, we project the layers to screen space, and there we decide, like, how large is it, and based on that we have some heuristics to decide on the strand count and the control point count. This is done with a compute bus that happens before. It writes to an indirect dispatch buffer. It is uint 4 for every bundle, so every bundle has its own dispatch. And the first entry is just the number of strands, and the set value, which is not used by the dispatch directly, is the number of segments, but this one is then read later on in the shader. So one dispatch per bundle reads X, Y, Z, and one workgroup per strand, which then reads the set value to decide on how many control points. So our writes happen to a G buffer because we do deferred shading, because it was just too costly to shade every single segment. So the problem here is that we need to compress this all into 64 bits. I first thought about maybe I can just use strand indices and then later on read the values for each strand, but that's just too much. Like, if you have 100,000 strands and then you have 100 segments per strand, and indexing all of that is too much. Maybe you have multiple grooms too. So what we did was we used 24 bits for the depth, and then we need the tangent, which we encode with this octahedron unit vector encoding. Then you can reduce the free floats to 2 floats, and then the 2 floats are quantized to uint 8 bits and stored. And there's also a styling coordinate, so that if you apply the styling functions, you need a coordinate frame that is consistent, and that is the styling coordinates here. And we also quantize them to even 6 bits, which seem to be enough. And there's even room for adding a bit of occlusion. So the right images with ambient occlusion, it adds a bit of more detail to the strands. So let's talk about this center versus conservative thing that I talked about. So if you do a single sample rendering, you see that you get a lot of these disconnected strands, like on the left side. And on the right side is kind of the ground truth, or the higher sample version, which does not have these artifacts. So how can we cheaply get rid of those. But first, like this is what a single sample would look like. The strand goes through the center of some of those, and those pixels are shaded. For the conservative rasterization, we shade all the pixels where the strand goes through. And then we try to combine those two results to get a anti-aliased version. And we do this very easily said by using the number of center pixels and divide it by the number of conservative pixels, and use that alpha then to soften, like we fill in the rest of the strands pixels and then use the alpha to make it a bit softer. And the cool thing here is that no extra step really is needed. It can be just be part of the filtering, compared to Huang's work, where they have an extra pass where they do this strand linking. So they use the tangent of the pixel strand with the ID, and then walk this tangent along until they find this one pixel on the right top, and if it's the same ID or so, then they connect it. And yeah, in our case, we don't need that. And I think this could be also interesting for hybrid RT, ray traced strands, where you do the first hit with a software rasterizer, and then you continue from there. So this is the result. On the first image shows the center sample rendering. The middle shows the conservative layer, and then the combination is on the most right. So yeah, there were also a few things that I kind of needed to fix to make a bit more efficient. So when you have a shadow map or a deep opacity map for these grooms and you remove strands, it could happen that some strands then that appear are somewhere inside of this volume and are then shaded darker than they should be. And my fix was to just, or our fix was to just move the strands that remain a bit further or closer to the camera, so that they are not shaded, that they don't fall like into the deep volume there. And we also do this by using a ratio of remaining strands versus total strands. Also, this is a comparison to a problem that appears in the original work of hair meshes. So they tried to argue that you can speed up this spline computation by moving a lot of that to the texture units. And the problem with texture units is that the interpolation is kept by 255 steps between pixels, and then this can result in these jittery artifacts for the strands. And at the same time, with the texture interpolation, you cannot extrapolate. So if you have kind of like a scaling slider, for instance, that moves strands maybe outside of the hair mesh bounds, then with the texture one, it kind of breaks down. And with our software-based approach, it doesn't. And for some reason, it's also faster than the hardware one. Yeah, but it was hard to actually validate this to the original code, because there is not really original code. So a quick example, this is a close look of one of the grooms on the left with a mesh shader approach, which is close to the original paper, and on the right with our software rasterizer. Besides the big speed up, our filtering also resolves some of these aliasing artifacts. There is still a bit of like aliasing in the middle of the groom or in the inside of the groom, but I never could finish that part. So when we move a bit further out, we can see that these aliasing artifacts increase with the mesh shader, and in our case, it's much better. And yeah, this is further out even with noticeable speed improvements. So a bit more measurements here. So for the software rasterizer, you can see that the filter, so the first line is without the filter, the second line is with the filter, and with the filter the rendering performance only slightly decreases. But you can also see that for the very far view, there's a big spike in computation effort. The reason I think is because we use the conservative layer where we render all of the strands into that. When the groom only takes up a very small part of the screen, then this is very dense on the atomics. So I guess there the problem comes from, but I never could evaluate that further. But this is solved by our LOD system, because that reduces the amount of strands that are actually rendered, and then this problem goes away. And yeah, the yellow highlighted row is actually our hero setting. When we look at the mesh shader based version, you can see that it is noticeably slower, and this even gets worse when we add the LOD. And the reason for that is that with the compute shader approach, we can use one thread in our work group per bundle, and with the mesh shader, the task shader can only do like the 32 or the what your work group size is, but it can only do the full work group size for a single dispatch, and that would be like one bundle, and that reduces a lot of unnecessary work for situations where the LOD does not really take effect. Yeah, this is like one of our examples with a lot of grooms. These are 500K strands, and it renders in about 9 milliseconds on a 5080. I wanted to use a lower tier graphics card, but it's really hard to get anything out of the ordinary in such companies. I could only choose between a 4080 and a 5080. I chose the 4080 and I got a 5080. Yeah, unfortunately, I would have loved to test it on a very weak GPU. I vibe coded a re-implementation because I don't have access to this code anymore. I will put this online sometime. I still need to make sure that it really does what our paper does. Visually speaking, it's close, but I think some of this synchronization stuff is not done properly. But yeah, if you're interested, you can come to me and I can then show you this on a laptop. Okay, thank you, and ready for questions.
Thank you for a nice talk, Lucas. Do you have any questions from the audience?
Thank you for the very nice talk. Really cool results. I was just wondering, from a practical point of view, how difficult is it to create a groom for your toolbox? Is it something everybody could do? Is there some samples or so, or is there some method to automatically sample grooms? And yeah, in traditional pipelines, it's very difficult. So I was wondering, maybe it's a little easier with that tool.
So it is actually pretty easy. You basically just create cubes stacked on top of each other, and you can then do multiple of these bundles, and then you have a bunch of sliders, which are these styling functions, and then you can curl them, and it's really just a matter of like adapting those sliders. It's already gone, but yeah, adapting those sliders. You have one for curl, one for fast frizz, and so on. So it's very, very easy, and you can like do it interactively. And I think there's also like room for even more styling functions there. Yeah.
Further questions?
I was wondering how you calculated the shadows and the occlusion that you have packed in with your data representation. Do you use a voxel representation, or do you rasterize that as well?
Okay, so the shading is using the deep opacity maps. Some of you maybe know. So it's kind of like a volume representation, but it's chopped into slices, and you then calculate the transmittance of the radiance there, and you store this into texture slices, and then you can, when you render a strand, you look up in which of those buckets the strand falls, and then based on that you shade the strand, and that's basically most of it. Yeah. And also like a more complex baked, unbaked. We used also a fitted BRDF representation, so where there are like the different lobes of the strands are basically pre-computed, like the R and the reflection lobe is one, then you have the transmittance, reflection, transmittance path, and and these are then pre-computed and used for shading.
Let's thank Lucas again. And our final paper is Environmental Volumetric Neural Shading of Clouds for Real-Time Rendering by Ricardo Lajos, Michael Dogat, and Prashant Goswami. Take it away, Ricard.
Okay. Is this audible? Good. Yeah, so we'll talk about clouds now. I'll start with some motivation for why we did this work, and then I'll briefly explain the relatable neural assets by Mulia et al., because it was a great inspiration for our work, and we based our implementation of their neural method. After that, I'll go through our approach, the neural model, how we generate the data set, and finally the rendering. And I'll round off with showing off some results. So when you want to put some clouds into your game, there are a few options. Maybe the quickest and fast way to get them in there is a skybox. It's boring after a while. If you start moving the camera around, you realize it's just a flat image. So you maybe put in some billboard approaches instead to get some parallax effects happening. But once you start flying around with the camera, you see, they are just flat images. So you have to do some ray marching to get a properly physics-based volumetric entity in the scene. But ray marching also comes with some, I would say, like drawbacks. It's quite intensive to render. So a typical way is that you lower the resolution, and you can see that sometimes in the final render also. Something you have to consider is the step length. How often do we sample the noise functions? And if you move the camera, sometimes you can actually get some artifacts when the steps move inside the noise function. Also something to consider is how big of an approximation you do for the light interactions. Should you do a single scatter or multi-scatter interaction? And if we look at some examples, I have some pictures here from Microsoft Flight Simulator. They are really nice, impressive looking clouds. But to me, they are immediately looking a bit low resolution. You see you have very soft features on the clouds. Let's see if I can point like you have these soft features over here, and the edges are quite soft as well. Similar here in a different shot, I would say this looks low res to me. And if you don't have a beast of a computer, you have to lower the graphics setting a bit, and then this becomes very obvious that you have a low resolution for the ray marching going on. So I'm going to share some vacation pictures now that I took. This is what clouds look in real life. So they actually have a lot of hard outlines, very sharp contrast, and also like high details in the contours when they're overlapping. Even close up, you see a lot of contrast, and even like the outline, it's not fuzzy at all. And that's not what the ray marching looks like to me. So this, I should also say, like not all clouds are this sharp. There are some wispy clouds also existing like this, but still you have this self-shadowing that gives a lot of contrast in the image. So this all made us start think, can we do something else than ray marching when we are rendering these volumetric clouds? So the relatable neural assets presented a really interesting approach. This is mainly for path tracing. And the idea is that you can bake in the material and light interaction into a neural model. You do it per asset, and then you can just evaluate this model and get the RGB values back. So they're presenting two different models, one for surfaces and one for fibers. So the one on top here with the tractor is the surface one, and then below we have the one with the fibers or strands. And something we can see here in the tractor is it has actually subsurface scattering. So okay, can we use this? Can we take this model, adapt it somehow, and actually make it work for volumetric clouds as well? So if we look at the model they present, so in the middle here we have the surface rendering, and then on the left, oh sorry, the screen is flickering here. And on the left we have this triplanar encoding they're using to I'm sorry, the screen is flickering in my face. Yes, so the idea here is that you take a point on the surface of the mesh you want to shade, and you send it through what's called a triplanar encoding. We heard about it a bit also earlier today. So the idea is that you take this point, you are projecting it on 3 axis aligned planes, and with these new coordinates you can read out from feature maps. So in their implementation they have 5x12, 5x12 resolution feature maps, and they're storing 8 features per cell. And these features are then fed into an MLP together with some information about the shading event. So in their case they're using the view direction, the light direction, and also the normal of the surface here. And out from this network they get 2 colors. So one is for the direct lighting, this one here, and then they have another color if the situation is such that you're actually blocked by the light. So when they do the rendering in their implementation, they're doing path tracing, so they're just doing Monte Carlo simulation and querying this MLP lots of times. But they also have some results showing like close to real-time performance. So jumping over to our implementation, this is the summary of our whole paper, and we will come back to this picture a few times as we are going through the different parts here. But we will start talking about the network that I've put down here. So the network looks similar, but there are some differences. So looking at the outputs first, we see we have the color of the direct lighting, and we also have the color of the indirect lighting. But the clouds, they are more semi-transparent in nature than the hard surfaces RNA is our renderings. We also introduce a transparency channel as an output. We keep the triplane encoding for the input, and then for the light, we don't have a light vector because RNA is doing like a single light point, and then they are sampling it many times. But we are having clouds in our scene, and we know like the light is coming from the sun, and we can actually use a more complex light model, like a full sky texture, to light the cloud. So we want to bake this light texture into the model directly. So what we put instead here is like just the angles towards the sun direction for a sky model. And then in our research, we saw that adding a thickness parameter to the network helps the network greatly to estimate what's the proper value for the alpha channel. And you can imagine if the cloud is very thick, then the alpha is high, like there is an opaque pixel. But if the cloud is thin, the alpha should be low. Okay, so we know what the neural model looks like. So how can we train the model? We use Blender to generate our data set. And the first step in getting our mesh is that we need to actually convert a volumetric entity to a mesh. So we use Blender for this. There are many ways to do it, and it's a bit out of the scope of this paper how you convert a volume to a mesh. But you can see the idea here is we're using the Walt Disney cloud asset, and we are getting a mesh surface out of it. So we want to recreate and get the needed input. So we have in Blender a setup with 2 cameras rendering from the front and from the back to capture the front and back sides. So these are the buffers we are generating in Blender. The first one is the full volumetric rendering, giving us the ground truth image that we're gonna test against for the training. And this one is using the Nishita sky model to light it. Then we have the front faces, and these are color encoded as RGB values. And then we have the back faces, and this is actually the camera rendered from the back, and then we have mirrored it so you can kind of see the inside of the cloud instead. And yes, and they're using orthographic projections, so they should be mapping quite precisely. And then the last buffer we're generating is this visibility buffer. RNA is doing this visibility test, and we want to see also, are we in direct contact with the sunlight, or is the cloud self-shadowing itself? Yeah. The data set generation, yes, we are generating with this resolution 1,000 frames and varying the camera direction and the sun direction. So we have the data set now, and then for the training, this, I'm not going into details, this we just took what relatable neural assets we're doing, but the main takeaway is it takes about 20 minutes on a NVIDIA A100 to train one asset. So back to this picture here. So we have the data set, we have the training. How does the rendering look like? So the renderer is a fully rasterization-based renderer. It's implemented in Vulkan, and the idea is that in a fragment shader, we want to color in our mesh with the correct values. So in this fragment shader, we implement the inferencing of the MLP, and we're using cooperative vectors that we also heard about earlier today to do this. To recreate the inputs, so we need the front faces and the back faces. We have a few pre-passes. So we first render the back faces, and then also render the front faces, so we can calculate this thickness parameter. And then to decide which color output we should use, we also do a shadow mapping pass from the sun's point of view, standard setup. And once we have all that, we can shade the surface of the mesh, and we hope to get something that looks like a volumetric entity back. And the final step is also to actually render the sky, and this has to match what we trained the model with in Blender, basically. So whatever we used in Blender to generate the ground truth image, this should use the same sky model. So for the results, we did an ablation study. We looked at different network sizes, varying the width and the count of the hidden layers. Then we also looked at the thickness parameter that we introduced. Does it help? Does it not help? And we also investigated whether or not the visibility test is needed for the clouds. It helped the RNA implementation, but would it help with the clouds? And the final thing I will talk about is also triplane encoding processing that we added to help improve the results. So looking at the ablation study, I'm not going to go through all the numbers here, but the main takeaway is that we have the different sizes of the network, and as we increase the number of parameters in the network, we see an improvement in the PSNR scores and an increase in the decrease in the flip errors. And something interesting to see also is that we have, this is in milliseconds, the frame time, is we have like real-time performance up until we don't have it any longer, and that's when the register pressure gets too high for the too big or too wide layers. So the model, the mesh that you saw before, it has a lot of triangles. It's like 1 million triangles, and it's a lot of triangles to render one cloud. So we also looked into, could we use a lower polygon model with the same trained neural model, but switch out the mesh for a lower poly version. And it works. I will show some results later, and then we can see here that we can gain even more performance. So it's the system works with a LOD system also. So I promised some results about the thickness parameter. So here on the left, we have the path traced reference image. And below, I also have just the alpha channel visualized with a color map. So here in the middle, we see what happens if we use a thickness parameter and on the right, if we don't use the thickness parameter. And what we see here is that certain parts of the cloud from certain angles will be very thin, and the network can't really understand this without the thickness parameter input. So if you're looking at this cloud from one side, it thinks these parts should be thin, but from different directions, it should not be. So we can see that the thickness parameter helps us with the rendering. Another thing is the visibility test. So once again, we have the path trace reference out here, and then we have without the visibility test and with the visibility. And they might look similar, but I will highlight some differences here. So you can see in these areas we are losing some details compared to with the visibility testing. And also we have some highlights here which should be fully shaded. So we can see that the visibility test for self-shadowing is also needed for the clouds. It helps us here. And I should also say that there is actually, we might be introducing some small errors with this. So trade-offs as usually. Yes, and the final thing is the triplane encoding. So the triplanes we are just storing as textures to read out in the fragment shader. And we can look at them and visualize them. So there are 8 channels, and here is 3 of them visualized. And what we see is that we're encoding a lot of geometry in the triplanes. And there is also a lot of high-frequency details and some blotchiness in the encoding here. And if we render a cloud, it doesn't come off well. But it looks nice with the cloud above the city. You could see that there is some blotchiness here in the cloud as well. So since these are stored as textures, we could actually just apply some mipmap leveling to it and blur them to get rid of a lot of the high-frequency noise. And if we do this for the cloud, we can see it looks maybe more like a cloud, less like noise. Yes, so we'll jump to some results of it in action. So here we have a cloud with the 4x64 MLP network, and the light is static, but the camera is moving around. So there is some semi-transparentness going on in the edges. There are some wispy parts that are transparent, and here I'm changing the light direction but keeping the camera static. Yes, and you can see the Nishita sky is working both in the cloud model and in the background. So here we can see the triplane filtering with the mipmap level changing. So it might be introducing some errors. We measured it. It does introduce some errors, but it looks better. And here we're seeing the high polygon model. So it's rendering about 230 FPS. And this is running on a RTX 4080. And this is the low poly model. So yeah, it doesn't look beautiful close up, but it works. Okay, and with that, I thank you for your attention.
Thank you, Ricard, for a nice talk.
Thank you.
Do we have any questions from the audience?
Very interesting talk. You just mentioned that you mip-map the latent textures. I was wondering, do you train the mip-maps, or do you do the mip-mapping during the training and render at different resolutions, or do you just assume that mip-mapping afterwards is fine?
Yeah, I assume it's fine afterwards. But it's an interesting idea. And also, why is it noisy? I'm not really sure. But I guess if you train longer, you will get less noise eventually. And I guess it would converge to something that it's lower frequency. Yeah.
Hi, this is super cool. I'm wondering, for the lower poly representation, would it help to expand it into a shell around the thing so that you have something more for it to kind of blend into transparency? Because it seemed like most of the artifacts were just at the edges, so it might be fine with a little more space or something.
Yeah, so I'm not sure I understood, but so the main point is that if you have a different mesh, you still need to recreate the same position for the MLP input. So the surface needs to be close to whatever the network was trained with. So if you move it too far away from the original surface, you will introduce more and more errors. Yeah.
Thanks.
Hi, thanks for the talk. So 2 questions. One, how do you deal with interactions between different clouds, or is that just...
Yeah. I haven't looked into it, but it should work fine.
Okay.
And you would have the shadow map, they would cause shadows on each other, and yeah.
Okay.
Yeah.
And any thoughts about if you wanted to animate these clouds?
Animate? Yeah. Yes. I mean, I've thought about it. I would like to do it. It would be cool, but you probably would have to have a bigger model, because you would need to introduce some type of temporal dependency, and you're going to need a lot more of parameters. Maybe you need to animate triplanes as well, and have slices of triplanes that go through the time variable.
Right.
Yeah. But
Okay.
I imagine it could be done, yes.
All right, thank you.
Thank you.
Further questions? So you have some LOD mechanisms here, like the polygon count of the mesh, the meat maps of the triplanar representation. How do these interlink, or could you have instance more clouds and have a
Oh, sorry,
sky?
I can't really hear you.
Yeah. So you have several LOD mechanisms here. Do you know how these interlink, or have you looked into, for example, more clouds and filling the sky with clouds and having more distant?
Yeah. No, I haven't had full cloudscapes in the scene, but it's definitely something I would like to try out. And there are many things that I have many ideas how to improve and continue working on this also, but yes, not yet.
Sounds like a nice direction.
Yes.
Thanks for the talk.
Yep. Thank you. What's on the schedule? Break? Yes,
Yeah.
coffee break.
We have a break now.
plug it in, see it on the confidence monitor.
Power.
I have some here.
Just to be safe.
We have the HDMI directly in front of you.
Hold on. Sorry, busy. Not multiprocessing here. Okay, page 1. Laptop set up. Microphone. The wireless. Oh, I see. I'm gonna have to carry it.
Yeah.
I was expecting something that is plugged into my desk.
Okay.
Okay. Well, at least I know where I'm holding.
Let me see. Maybe.
Go here.
I gotta get you some space over here. Okay. So what I could do, I have a clicker as well. If you want to use that.
What does that do?
Clicker, so you don't have to come over here and turn the slides manually.
How does that work?
I got a remote right here for you. So look, that's it. So what happens is basically push the green button forward, red button is backwards.
And how does that work?
So I just have to plug it in.
Oh, and
once
the
you-
USB
do
port?
you have a, yeah, do you, is it a slideshow or?
It's a PDF. You have a USB A port, or you can use this. It's an adapter.
No, that's okay. I got it.
Or you got USB-C.
All
to work for a PDF though. I thought it had a PowerPoint. Let's see. Oh, yeah, that's okay. All right.
Hey, cool.
Now
Thank
you
you.
can walk
Great.
around and get, really explore the space.
All right. I am good. Make him sit down. Shut up.
So I'd like to introduce our next speaker, Eric Lindholm, who held the title of Senior Distinguished Architect and Master Inventor at NVIDIA, where he made key contributions to the invention and the evolution of the first GPUs. Today he'll be talking to us about programmable graphics icons, looking both backwards and forwards. Thanks.
I lost the full screen here. Hold on. Where is it? Where did you go? Sorry about this. Anybody know where Adobe has the full screen option on PDFs? I don't remember. Here, actually, no. Hold on. Reload. Tough start. Okay, so my name is Eric Lindholm, you all know that. I've spent a lot of time in Silicon Graphics and NVIDIA, working on the high-end graphics hardware for the respective companies. I was asked to give this keynote, and so here I am. The abstract, just to give you a quick summary, the graphics pipeline, which you all know and love, has evolved over the last about 45 years from a simple fixed function hardware into a much more flexible, partially programmable pipeline, which I strongly object to and have been for many years. This talk will review some of the major changes over time, focusing on Silicon Graphics, the inventor of the geometry engine, where I've spent the bulk of my career in the area of geometry engines in NVIDIA, and some ideas for the future. And I will bum around a bit on the sides to inject some personal anecdotes. I want to thank David Lupke of NVIDIA and NVIDIA for permission to discuss my work done at NVIDIA Research, because I am retired. And I also wish to thank Kurt Akeley and John Montrum, who I have worked with for decades and decades, for their historical insights. And the views and opinions expressed in this talk are strictly my own, I promise you. And then SGI, of course, can't complain much anymore anyway. Outline Silicon Graphics Part 1, NVIDIA GPU Architecture Part 2, and then research where I could do whatever the heck I wanted without worrying about the reality of the cold, cruel, hard world. Starting with Silicon Graphics, and I got this from Kurt. Kurt is sitting there, he's a graphics god from the Silicon Graphics days. So if you have any questions, you talk to him. Silicon Graphics was founded in 1981 by Jim Clark, professor at Stanford, and 7 graduate students / staff, of which Kurt Akeley was one of those. And he designed the first geometry engine back around 78, 79, the prototype, I think. And it was a specialized floating point processor for graphics processing, specifically the transform pipeline, which encompassed the matrix. This is your position, X, Y, Z, W, times the viewing / projection matrix, a clipping subsystem, and a scaling subsystem. And these were custom chips. They were not particularly sophisticated by modern standards, but at the time, they were, I think, something rather outstanding. And the rasterization was custom hardware with a bit slice processor on the pixel side. And the pixel processor at this point in time, as far as I can tell, was way more programmable than the geometry engine was. And as far as I know, it was never really exploited, and I'll get into some of the reasons for that. But it's a peculiar reversion of what I would normally expect. So I got this die some years ago from another ex-SGI worker. And this is almost original geometry engine die. And I would love to learn more about it, but Kurt says he doesn't quite remember what it was. The graphics pipeline, this is actually a more modern pipeline, but you have your host interface feeding a geometry engine for the vertex processing, setup of triangles, lines, points, raster subsystem, pixel processing, and the raw or raster operations processor, or what SGI called the IMP. And I think everybody here, I presume, has a pretty rough idea what a graphics pipeline looks like, right? Anybody who doesn't? Good. And of course, vertices make triangles, you rasterize a triangle, generate pixels, and life was good. SGI, around 87, started shipping their second generation system, and these custom-built geometry engines were replaced by 5 WATEC floating point processors at some cost, evidently. They were impractical to use the previous designs. So now we're getting into the third-party provided geometry engines. And I'm sure they weren't actually custom built for graphics. They were simply floating point engines, but they were highly programmable. And now the IMP became custom hardware and was no longer seriously programmable. And the problem with this, I worked on some of these systems later on, was that all the cruft code went in the bottom of the pipe that was programmable, which was the geometry engine. I actually spent some time once writing a concave polygon decomposer in the geometry engine. That kind of stuff makes it really difficult to build custom hardware when you have to support functionality like that. I heard that Silicon Graphics once did expose a geometry engine to a third party for custom code crafting, and it was not maintained and not tested. And as we all know, when that happens, the code rots. And SGI would have a new geometry engine every architecture, and who's going to port the old code to the new system? And it was simply impractical to maintain. There was no infrastructure in place for exposing the possible programmability of this pipeline. I joined SGI in the summer of '89 in the Advanced Systems / Graphics division, and I wrote code for the geometry engines of the Reality Engine and the Infinite Reality, and some other future stuff with the Geometry 11, the G11 chip, which was for the Infinite Reality, and Quality was the next generation after that. So here's a picture of the team, because I want to give credit to the people I have worked with. There's not much of that going on in this world, I discovered. And here you will see Kurt, the way he used to look when he was a few months younger. And that's me, and here's John Montram, who interviewed me, I believe, at SGI back in '89. And I spent my entire career of 35 years working no more than one building away from him. And I play golf with him as well. Then came the next generation, VGX, VGXT, had the texture mapping. Now we have a TI geometry engine, totally different from the WATEC. It's a 4-wide SIMD, 2D pipeline, 8 chips. Then the Reality Engine follows that. Now we have the Intel 860 XP chip, 12 of them. I wrote lots of code for this baby. For those of you who like, project nicknames, VGX was called Stay Puft. Skyrider was the VGXT. Then this was the Reality Engine. And then the Infinite Reality from 1996. We had a G11 custom designed by SGI for geometry processing, 4-wide MIMD arrangement. I did lots of assembler on this one. I don't think we had a compiler for it, actually. Souvenir wafer, and Kona was the nickname of this one. And Bali, the next one that was never shipped, followed the same naming system. This is from SIGGRAPH 1996. Here we have Mark Kilgard, who you heard talk just a little bit earlier. And there's John Montram yet again. I don't know where Kurt was. Maybe he was partying. He's a founder. He doesn't hang out with us lowly engineers, perhaps. And there's some pretty famous people in here, if you follow the field. So So every SGI architectural generation had a new geometry engine, usually from a different company. There was no forward compatibility. So exposing something to the outside world was really awkward. This is not like a CPU by Intel where it's forward compatible. You can run x86 code from 40 years ago. It still probably runs on an x86 chip. And if you want to go programmable, you can't just do one part of the pipeline. I mean, what's the point of that? You need at least two of them to cooperate, maybe even three. So SGI had one programmable chip, and unless we, or they / Kurt, whatever, implemented a much more flexible raster or an IMP, as we called it, there's really no point in making vertex programming flexible and still drawing your text blend pixels at the bottom. The reason for all this was SGI was extremely performance driven. Every generation, I think, had to be 10x better at something. It was either 10x better in features, or it was 10x better in peak performance. You don't just reuse the old stuff from 3 years ago when you want a 10x improvement. It was just impractical. So we got a lot of cruft in the geometry engines. I coded a fair amount of that cruft. I know it. But as I say, the tree of programmability was obscured by the forest. There was this beautiful core of the original geometry engine buried inside these modern geometry engines. And that was what I loved doing. Not the craft, but transforming vertices. That made me really good. It made me feel really good. However, at the end of my career at Silicon Graphics, this is late 90s, there was work going on in multipassing the graphics pipe. So we're not discussing exposing parts of the internal guts of the graphics pipe. We're going to multipass the whole pipe multiple times and build up special effects. And there's a paper called Interactive Multipath Programmable Shading that you can look up for how this was to be done. Yeah, so they broke down complex shader effects into multiple sequential passes through a standard non-programmable graphics pipeline. Let's see here, sorry. So moving on to NVIDIA GPU architecture. I'm going to skip over this very, very briefly. Started 1993 by Jensen, who everybody knows today, Chris Malachowski and Curtis Cream. And NVIDIA was one of 70 startup companies chasing video gaming for the PC. I joined NVIDIA because I wanted to work on mass volume, mass market computer graphics. And Silicon Graphics was high-end, very expensive stuff. In the end, only two companies survived, up to a certain point at least, NVIDIA and ATI, and ATI was acquired by AMD in 2006. Just before I joined, there was a massive layoff at NVIDIA, the year before, in fact. When I joined, my employee ID was number 125, but there were about 65 employees, so 60 went missing somewhere. So it was a small, scrappy, somewhat precarious company. A lot of fun to work, but a little bit scary at the same time. And Jensen's plan was to keep schedule and win the benchmarks regularly to get business. And this was unlike Silicon Graphics with 3 or further boards, big boards. We should know what size they were. Kurt probably knows. They were big boards. We're talking about a single PCI card, AGP card plugged into the PC. And it supported everything. You just slap some memory into it and off you go. There was no geometry engine, however. And this is my old Riva 128 card that I bought probably 1998, beginning of, end of 97. And Riva stands for, as you can see, the Real-Time Interactive Video and Animation Accelerator, I was told. Let's see here. So we've got that. Anyway, it was a good chip for the time. It kept the company alive. Very fast, a bit sloppy, but that's what the company needed. In the spring of 1998, Intel comes out with the i740, and it's the old, we're Intel, you're out. Not a hype. They've done that multiple times. I don't enjoy it. Nobody does. It was a reasonably good chip, but it didn't quite make it, fortunately for us. And now the graphics wars are in full swing. We have 3DFX, whom some of you probably know, Feed Labs, ATI, Intel, NVIDIA, Rendition, among others. I worked for Dave Kirk, who you see there in his military regalia. And yes, his business card actually said Minister of Armaments on one side. I think it said Chief Scientist on the other, his more polite side. And, you know, I don't think you have a boot magazine anymore. This was the monthly What's Hot in the PC Graphics Space magazine. And they ran all kinds of articles about the latest and greatest, you know, graphics card you could buy. And it was a big deal to win the benchmarks back in those days. People went out and asked for your graphics. The TNT shipped in the fall of '98. Really good chip. Still no geometry engine. And then NVIDIA, I shouldn't say we, but NVIDIA IPO'd beginning of 1999 at $12 a share, market cap about $800 million. I think it's at least doubled since then, fortunately. And here again, we have Eric, and there's John Montrum again. I just can't get rid of this guy. From me. Actually, he joined before me. I shouldn't say that. He can't get rid of me. So in December of '97, I started work on the NV10, what is now called the GeForce 256. And my job was to add a geometry engine to the standard pipeline. We didn't have one yet. They used a CPU for all the transformer lighting work. And the goal was to exceed the infinite reality at 10 million polygons per second. But now it wouldn't be a large plug-in card. It would be a unit inside of this die. And I learned well. Silicon Graphics was a great place, really sharp people. I learned an awful lot of stuff from these guys. So I knew what to do, but that doesn't mean you know how to build a small unit on a die by yourself after working with a team. It was a little bit scary stuff. But, and I want to mention that Simon Moy, my friend, we still play golf together, and me, we did the T&L blocks of the 10, 20, and 30 generation chips. There were two of us. That was it. Everything we did, except the driver side. I'm not going to claim that. So with two people, then you get 6 months to get something finalized. You can't play games. And honestly, I really had no idea what to do anyway, so that was okay. But you sweat bullets, basically. And the operations are pretty basic. The vector multiply add, dot product is cool, reciprocal for perspective divide in projection, and the reciprocal square root for vector normalization, for lighting mainly, and the power function for specular lighting. That's what you start with. I actually built two units. There was a transform and a light unit, and they were in series with each other. Doubled my performance, couldn't argue with that. Plus the required precision of the units was different. Transform, you want FP32. Lighting generates RGBA, 8-bit integer values. You don't need FP32 for that. So my idea was, okay, great, I'll write a bunch of code. We'll chunk it on the CPU, download the current modes we want to execute, and bingo, just build a nice little processor. Unfortunately, around Christmas '97, I had a conversation with our CTO, Curtis Preem. Now, I've been there 4 months. Even if I had 10 years of experience, I can't argue with the CTO of a company I just joined. And he promptly informed me that we cannot download microcode. Not allowed. And the reason for that was future compatibility, which he really cared about. He wanted the next chip to run on this chip's drivers. You swap the card out, plug the next generation card in, and it ran at least as well as the old card did. Now, if you're writing microcode, you have to be compatible with your compute block to make that work next time. And that's a huge burden when you're trying to do, STI to 10x every couple of years. We're doubling performance every year, easy here. It was not it was awkward. I left the meeting rather lost and dejected, I have to admit. Didn't know what to do. But I thought about it. That's what you do when you're an engineer. And I thought, okay, great. So the graphics pipeline, the whole pixel, the whole vertex setup, pixel, raster operations, is a pipeline. One before the other, it never changes. Inside of TNL, the vertex processing, there's another pipeline that you can write that starts off with position transforms, vector transforms, do the lining, and you can write that as a pipeline by itself. And if you do that, you can then say, okay, you want to do this part of the code if these modes are on. If local viewer is on, then I want iSpace position, for example. So you can write this if, do a bunch of work, if, do a bunch of work, if, do a bunch of work, continue this, and generate the whole transformer lining pipeline. So the idea was, take those if statements, make predicates out of them, and then have the hardware walk the predicates in the sequencer so that you would generate this long 150-odd bit vector of ones and zeros, and you would execute the assembler instructions that had a 1 in front of them. The zeros you would skip over free. So there was no conditional evaluation. It was just next math, next math, next math, skipping over this template, as I called it. And I asked Simon, hey, can you do this? This feels difficult to me. You're going to walk 150 bits, finding the next one every clock, including doing some looping, because there's 8 lights, and maybe 4 textures. So you have to get to a certain point and say, oh, it's a loop here. Go back, auto increment a few registers and memory locations, do the next one, and continue doing this. And he came back and said, yeah, no problem. And I have to say this, I have been so incredibly impressed by the hardware engineers I worked with. You can go to them and say, I had this really hard thing, I don't know how to do it. And they'll say, yeah, I can do that. And then they explain how, and you go, wow, that's really clever. And so, talk to your coworkers. They see things you don't. Anyway, the GeForce 256 shipped October 1999. Performance did exceed the IR at about 1/1000th the cost, based upon John Montrum's calculations. It took about 6% of the die. So now we've gone from a card, yay big by yay big, weighing many, many pounds, to 6% of a die. And it took 4 years. And to me, this is a worthy successor to the original geometry engine, which is why I started with the SGI and the original geometry engine, because it did the core operations, not the cruft, not the swampy stuff, and this unit just did the core things. Again, some good favorite articles from the old days. The chip was very successful. 3DFX folded, leaving NVIDIA and ATI. This was in 2000. Companies were dropping dead left, right, because they couldn't keep up. And a lot of this was because a lot of the people I worked with came from SGI. We had done this at the high end. The $100,000 plus graphics pipelines were now being ported down to single chip for the consumer market. And even ATI had their fair share of SGI ex-employees. So it was a wonderful company. Talk to Kurt if you want to know more. So NVIDIA defined a GPU as a single chip processor with integrated transform lining, triangle setup, clipping, and rendering engines capable of processing a minimum of 10 million polygons per second. By that definition, which is somewhat self-serving, I admit, this was the first GPU. And you can't argue about that, no matter what you think. By that definition, it was. If you don't like the definition, we can argue outside. But it was very much a fixed function processor. And NVIDIA is still very, very proud of the GPU. As it says here, the world leader in accelerated computing. NVIDIA's invention of the GPU in 1999. This is what it starts by saying. And so what does G4 stand for? I found this article. Stood for Geometry Force originally. So again, the TNL unit is part of the name of GeForce. And this is from 2002. However, I know you're here to hear about programmable pipelines, so why am I wasting my time on this stuff? The TNL block was as far away as one can imagine from being programmable. It was fixed function like you wouldn't believe. The unit had no software. It was burnt in to a template ROM that had to be modified by the sequencer in real time to generate real code. Adding anything was a respin. You couldn't code around anything here. It just did what it did. But it was very small and fast, and it was exactly what I would need for the next chip. So the first programmable GPU, NV20, the GeForce 3. So why did we do this? And there's three main reasons that I can think of. One, I was told at the time, game developers didn't like fixed function. It was too standard. Anybody could do it. There was no special look for their games. It was standard, generic graphics. The other thing is we wanted to enhance pixel effects as well. And it was really hard for me to modify this unit. It was pushing the limits of what was possible in hardware timing with this. The sequencer was rather tricky. And you could add more mode bits. Here's another mode for this special pixel operation. And then you had to expand the sequencer, you had to expand the template, and you had to redo the sequencer. And it just got complicated. For its time, it was great, but it had no future. So I started with the NV10. Of course, that's what I had. I had the hardware code template in the hardware, which was the simplest thing I could possibly imagine to run the Vertex pipeline. It was where Vertex shaders started, this template, because it did everything I needed for Vertex processing, but it just was not friendly in any way or sense to a programmer. Couldn't even get to it. Basically, starting with that, I rounded out the unit because it only did what it had to do. So you had to build a shader model around it. You had to make sure that all the combining this mode with that mode and your swizzling, your white masks and everything made sense to the programmer. And I was allowed to download microcode this time. I think somebody talked sense into Curtis. Otherwise, this would not have happened. And so Vertex shaders were born. We presented the design, and in fact, where's Mark Hilgard again? There he is back there. He was on the paper with me on the Vertex shaders. He was Mr. OpenGL at the time. Maybe he still is, I don't know. And also, it went into Microsoft's DX8. And where's Charles Boyd here? There he is. If you want to talk about DX7, DX8, DX9, DX10, maybe talk to Charles. He was the guy at Microsoft. He knows all about the politics and how this stuff, how the hardware moves into the Microsoft graphics layers. This was carried over into the 25, which was a 6-month modification or whatever it was, and the Xbox chip. And the Vertex shader, you can look at it. It's really basic. You got some moves, you got some adds, multiplies and adds, dot products, 3-term and 4-term dot products, dot product, reciprocal square root, a lit function for doing the lighting equations in OpenGL. But it was very flexible. It was not in any sense a Turing-complete processor or anything like that. But it was born on what was absolutely required to implement the OpenGL transformer lighting pipeline. And we did support rudimentary pixel shaders on GeForce 3, and I think the most popular effect was water reflection. So if you played Xbox games, maybe that's too long ago for most of you, but water reflection was a big deal. That was one of the holy grails of graphics in the 90s. Reflecting water off the waves. It was right next to fog shading at the pixel level with 2 holy grails. John Carmack, who you probably heard of, said Vertex programs are probably the most radical new feature, and unlike most radical new features, actually turn out to be pretty damn good. I'm human. I can't resist hearing a comment like this because, you never know. Anything can happen when you build hardware. It may be a disaster or it may be loved. Let's see, some articles on GeForce 3, completely reinvents visuals in 3D games. this was big stuff at the time. So now we have two programmable blocks in the pipeline, the vertex shader and the pixel shader. And things really haven't changed much since, let's call it 2003 timeframe. Yeah, we've gotten a few other shader types built in, but it still looks fundamentally like this, which is really unfortunate. If we look at the number of vertex and pixel units in the NVIDIA chips, so I think you can read this, hopefully, if you're nice. You can see that the vertex units went from 0 in 97 to 8 in 2005, and the pixel units went from 1 in 97 to 24 in 2005. If you add them up, you've gone from 1 to 32, 32x expansion of hardware resources in 8 years. And this was unfortunate. It kind of made sense at the time because, yes, they were similar, these units, in what they did, but not how they did it. The vertex units were optimized for pure math, low latency math operations. The pixel units were optimized for text blend. Fetch a texture, wait for memory to give it to you, then do a math. And so they had very different construction, and there were different teams working on them. There was no one team building both. There was a vertex team, there was a pixel team. And they didn't talk beyond the point of making sure they could feed, vertex could feed pixel the stuff it needed. And the serious problem with this progression is that load balancing was crap. You're looking at the MD47 at the bottom, 8 vertex with 24 pixels. Okay, we're building for some balance, some triangle size. How many, there's 3 vertices per triangle, how big is the triangle? That's how many pixels you need. If the triangle is huge, your vertex units are happily going do-do, da-da-da-da, and waiting for things to happen because you're pixel bound. And if you have small triangles, the vertex units are stuffed to the gills of the vertices, and pixels are kind of taking their sweet time because nothing much is happening. So it was great if you had that perfect size triangle, but no game ever did. So, we knew something had to be done. And we also didn't know what about shader complexity. When we started shaders, we're going, okay, vertex pipeline might be about Yale on pixels, they're very important. It's going to be short. And sure enough, people go, hell no. They start running monster shaders the first moment they get, and then your load balancing shifts again with the length of your shader code. So on the vertex side, I was a one-man team mostly, which was really nice, but I did have to admit I was eyeing that pixel type because I loved floating point processing, and they had way more than I did, and I was jealous. So I did what I could on the vertex side, and also because it was a brand new unit, I knew it inside out, there was no friction involved, I just did what had to be done. The pixel side, it evolved from, I guess, the Riva 128. So you're doing a text blend, as I said, you fetch a texture, you wait, you do a bit of math, repeat until you're done. And it wasn't particularly efficient at the new shaders. So it needed a rebuild. I wanted more, and they needed a cleaner architecture. GPU, that was a big deal for a little while, before shaders became much more interesting, is the use of a GPU to perform non-graphics processing. Now, the GPU is a massively parallel processor, but it was not designed for non-graphic tasks unless you draw triangles and encode your work as triangles and pixels. So they drew an interest in using this massive resource to do general purpose parallel computing. And this, again, was done by casting problems into a graphics framework, which was cumbersome. The high-level shading language CG. Now, again, we have one of the authors, Kurt, here. Mark Hilgard's over there, and there's Bill Mark. I think we have 3 of the 4 authors in the room from that paper. And Chaz, were you involved in this as well? Okay. So This was done with Microsoft, and it allowed developers to use higher level shading code instead of assembly, which of course was a good deal. And then there was the Brook programming language, 2003, and that was an early attempt to abstract away the graphics pipeline to harness, again, the massive parallel performance of GPUs. And that grew out of Stanford, I believe, Brook, right? And that's where Ian Buck came from, who is one of the foundations of CUDA on the software side. So there was a demand for something more. So the writing was on the wall. We saw this coming. It was no accident. It was time to design a unified shader architecture that would solve most of our problems. Load balancing is much simpler when you can do whatever you want in your unit. It's a scheduler problem instead of being a hardware problem. So I started work on the MB50 in summer of 2002, and I was the one and only architect for that summer because it was designed in parallel with the MB4X architecture. We started it really early. We knew it would be a lot of work. And this is how I looked at it. It was going to be the fastest geometry engine ever. And in early 2003, the MB50 team started to accumulate because this is not a one-man job, not even close. We needed a real team of specialists in different areas. And one of them, John Nichols, compute architect, is with Ian Buck, the founding members of CUDA. And he worked on the architecture side, Ian more on the software side. So my responsibility was the unified shader core, what became known as the SM. So now we could, in theory, work on multiple types of shaders with this architecture. The first problem was how to pack the work. And this is like week one. You sit down at a desk going, hey, I'm doing a unified shader architecture, cool. Hey, what is it? What does that mean? And the first problem was, great, what am I working on? I want to do pixels and vertices. There actually was no compute yet when I started the project. It was just do a graphics processor at that time. So pixels work in 2x2 quads for derivative reasons in texture fetches, while vertices tend to be loners. And obviously, to me at least, you pack 4 vertices or you have 4 pixels. Then you can work on units of 4 on one or units of 4 on the other. But I didn't like the amount of overhead in doing this. I wanted to do more than 4 units in parallel. So the question is, how wide should I go? And after a chat with Simon Moy, the TNL hardware engineer, he said, at least go 12 wide, he said. That should amortize out all the overhead of your processing units. And that, of course, was running out to 16 immediately. So 16 was the original design, very, very, very early, of course, of the MB50. And that was 16 vertices or 4 pixel quads. Now, if anybody here has programmed the MB50, which maybe a few of you did, you might remember that vertex warps were 16 wide, not 32. And this is where it all started. And this 16 wide evolved into the warp. This is how it started. And I could tell you exactly what happened, but I didn't do that choice, so I'm going to skip it. Ask the guys who did. And then the second big problem was, how do I schedule the work? So I liked the idea of math-heavy vertices with short latency, hiding texture latency for pixels. If they're going to wait hundreds of clocks to get their texture data back, let's run some vertices for free. So I like the idea of fine-grained multi-threading. Each unit could work on both vertices and pixels at the same time. Now you could design something temporally or spatially dividing units that would do one thing at a time. Maybe you build 12 and 8 are doing pixel and 4 are doing vertex and you move the line between them. But I didn't like that. It didn't feel very cool to me. I liked the idea of mixing them up and employing non-correlated work to improve the performance of something else. Vertex and pixel, in other words. And the key thing of all, always, is pixel shader performance. You know, CUDA came along, Vertices are cool and all that. If your pixel fill rate sucks, you lose the benchmarks, you're in deep trouble. It was a GPU. So in the spring of 2003, we were discussions with Sony about the PlayStation 3. And a lot of the early ND50 team is actually in this picture. And there's me on the left here side. John Nichols I marked out because I feel he deserves more recognition for what he did. I don't think his name is well known. You wouldn't have Compute and CUDA without John Nichols being there. There's John Montrum again, and lo and behold, on the side we have Mr. Kilgard, who seems to hang around me as well as John does. So I've known some of these people for a very, very long time. The MD50, also called G80, I don't remember why we changed it, was an amazing amount of work. I spent years working on ASM, mostly on the instruction set, the data paths, and scheduling. You know, as I say at the bottom, there was 12,000 threads in this baby. You can't just let them run amok. It wouldn't work very well. And what I enjoyed the most was throwing out the old pixel pipeline and combiners. I never liked them. They had ancient origins. You know, this was my new baby, my new TNL engine. Now, to be truthful, I threw out the Vertex units as well. This is a brand new unit that did both. It superset of everything. And it was a very different chip from anything that I know of has been built before. And it laid the foundations of the current AI boom. And I feel it's the most important chip of the 21st century. It's caused a huge change in everybody's lives and will continue to do so in its descendants. So I coined the term SIMT. You can blame me for that term. When we wrote that paper in 2007, David Kirk insisted we give it a new name that wasn't the same as the old names, and I came up with SIMT. And then I want to acknowledge Brett Kuhn, who did most of the SIMT divergence work. I didn't do that. And so every time you are happy or unhappy about the divergence branching of the NV50 or the subsequent generations, you can thank Brett for that. John Nichols named the units, the SM, the streaming multiprocessor, the SP, the streaming processor, the TPC, the texture processing cluster, and the warp. That came from his mind. I was asked to name them. I said, don't bother me, I'm busy. So they went to John. But I did get to name the GPC for Fermi. I figured I got to put one contribution into the naming space. This is from the paper, the Tesla paper, which I recommend you read if you haven't, showing the basic ND50 architecture. And all those little boxes that you see in here are SPs, and these are SMs paired up, including texture pipes and memory. And the work basically loops around, you know. Vertices go through, go out into the raster subsystem, comes back as pixels, go through, goes down to raw. In 2006, AMD acquired ATI. NVIDIA was the last one standing. The graphics wars were over. Intel still attempts a new graphics effort every 10 years, ... I continued my work on the SM and GPC for the Fermi architecture, which came next. And this architecture, the 580, was used by Dr. Hintons in the ImageNet 2012 competition. And unfortunately, John Nichols passed away the year before, so he never got to see what he accomplished, unfortunately. But this was the catalyst for the modern deep learning boom. And as NVIDIA can attest, business is booming in GPUs. We had geometry shaders, then came tessellation shaders, but they kept on, I wasn't involved in this particularly, but they kept on constraining programmability between fixed function stages, which was really annoying, I thought. And then mesh shaders came along, and this limits the flexibility of a possible future graphics pipe. So in 2011, there was a publication, High Performance Software Rasterization on GPUs, that used CUDA to do a graphics pipeline. And there clearly was an unmet need out there, or you wouldn't be coding without the graphics pipe to do graphics. It tells you a lot that you're not doing the right thing anymore if people are trying to get away from you. I didn't like the multipassing of the graphics pipeline. I disliked throwing it out and going to CUDA because there's huge efficiencies in our fixed function units. I wanted something different. So at this time, this is around 2013, the GPU group had gotten too large, NVIDIA was successful, and everything grew. There was teams everywhere, paperwork. The work got not particularly interesting. I spent many years in a small cowboy town in the West, and now I'm in a big city where there's paperwork and police everywhere. It's kind of boring. Peacetime was boring, yeah. I left GPU architecture in the fall of 13 and joined NVIDIA Research. And my first project was assisting the ray tracing effort that shipped some number of years later. I spent a lot of time in research thinking about work creation and queuing systems for more flexible processing of data. So finally, we're getting to the real topic of this talk. I hope you're not sleeping. NVIDIA Research. So what I wanted was a much more flexible pipeline. And again, this is me. This is not NVIDIA. This is what I did for fun in NVIDIA Research, exploring this space. I wanted to treat fixed function hardware the same as shaders. Any part of a pipeline, if you look at the traditional graphics pipeline at least, could be done by traditional stage, the fixed function, raster let's call it, or setup, or by programmable shaders. A pipeline should also be arbitrarily rearranged as desired. Why do you want raster before pixel? Maybe you're a genius and you want to do raster after pixel. I don't know. I shouldn't tell you how to do things. So no fixed stages and no fixed order of stages. And this, what I wanted fundamentally was to be able to use a current generation GPU to model a next generation GPU. Let's say NVIDIA decided that rasterizing circles was the new cool idea for the next architecture. Well, write a shader, bypass setup and raster into the SM, rasterize your circles, and feed them back into the pipeline to proceed normally. Replace what you have to, enhance it, experiment with it, design the hardware, and go back to normal. Yeah, and then evolution would take over. Once you can do this, if a shader stage is better than a fixed function stage, next time, why throw it out? Save the gates. You can do it in software now. There is no more vertex units. There are no more fixed function pixel units. They were thrown out as being impractical. So if a shader was important, because you have a new idea, you add a new shader, whatever it does, and it's the best thing since sliced bread, then you take that shader and throw it into a hardware unit next time. And now it's maybe 10 times faster, which makes everybody happy. Because you don't want to cruft up the graphics pipeline. It's supposed to be what it does really well. And if you can do it in another way, then you shouldn't have it in hardware. I disliked intensely graphics versus compute narrative. I wanted something new, something both. I want the superset of the two, not A versus B, but A plus B. So I wanted efficient local word creation and consumption. Support for global word creation and consumption was also important. Support launch of threads, warps, and CTAs from the same queue. This is the superset. If you want to launch a thread, you can launch a thread. Now, you may pad it up to a warp. There's certain realities going on. And if you want to spin off, I want 13 warps, thank you, to work on this problem, then you ask for 13 warps for your problem. And then you go back to a single warp for the next command. And the whole goal of this was to do, propose hardware enhancements for some future next generation architecture or whatever. So I called it the queue manager. It was supposed to be, hasn't been built as far as I know, a fixed function unit. Can't win them all. But it owns queues, controls queue scheduling and queue commands. And then you have execution resources like the SM, the texture pipe, setup raster, ROP, to deal with queue data. And this is very important. The QM deals with commands. Your super wide, super powerful units deal with data in the queue. I discovered while experimenting with this stuff that instruction fetch and issue is incredibly expensive on GPUs. If you have 4 or 5 warps spinning, waiting for something, querying, you can tie up a huge fraction of your issue bandwidth on wasted work. Because we're just going, is this free yet? Is this free yet? Is this free yet? And it was really annoying. So I wanted to offload all those kinds of spin loops onto a fixed function hardware unit that wouldn't disturb the warps. And this also allowed me to, instead of having 12,000 threads beating up on a poor memory location, I could hierarchically funnel the requests in a much more intelligent manner. The QM controls the command pop process. So only it is allowed to pop commands off a queue. It's not allowed for warps to do that, and I'll explain why. And even if a unit wants to open a push, like an output queue, then it would ask the QM for the requisite work to set that up. It would get pointers back and simply store the data using those pointers. And then you should go to sleep. If you're waiting for the QM, which could happen, you shouldn't be spinning on your return message either. So there should be a way for warps to go to sleep until they're woken up. So this is a simple drawing I've made where the QM deals with the commands going sideways, and these units deal with the data in a vertical direction from memory. So here's a pipeline example. And this is part of my simulator setup. I wrote lots of simulators, big simulators. So here we have a vertex geometry queue. This is now a proper queue, and this is in software, of course, a host software simulator that requests, or rather the QM hardware scans the queue, finds work. It knows the pointers. It knows how full the queue is. It knows the priority of the queue. It decides what to execute next. It looks at the top of the queue, gets some commands out of it, and says, oh, this goes to the SM, launches a few warps on the SM to get the work done. The SM does the work and gets back, and then that goes down to the setup raster queue. So the SM would push the data to the setup raster queue directly. And then that would go through the QM again to set up raster hardware if you had the hardware. But I could just as easily have told the QM there is no setup raster. The SM is dealing with that. Now, the queue doesn't know where it's going. It just asks to get this operation done. The QM decides, oh, this unit can do it, or that unit, I'll pick him. Or there's only one, it's got to go to him. And there's also a TRAM queue. You can do some really fun stuff with the queues, it turns out, when you play with them, that are not really queue-like, but they're really cool things. I don't know if I have time to talk about it, unfortunately. So what's the interface between stages going to be? Well, it's a streaming data pipeline, really. And, working on vertex units for many years, I've watched the command stream come in. I know what's in it. And the easy choice was to use circular queues. They're pretty common, no big deal. So the queue manager deals with circular queues, either for pops or for pushes. And the processing stage deals with that through the QM. So we have many different types of commands with various sizes of data. Sorry, I'm colorblind, but I think that's a blue color, isn't it? The commands. I just pick what I can see well. Data is the white. So here we have a command stream. We're looking at command A with some amount of data A. And then comes command B, command C, command D, D in a row, maybe 3 vertices or something. So the spacing is awkward. If you want to pack things in a SIMT, warp, how do you extract out the commands? It's a very, very awkward problem. So yes, you could make all commands have the same data size, so you can step on the commands at a fixed spacing. Or you could use separate queues in theory with synchronization, but that's really ugly. So what I did is I have 2 queues. Every queue is actually in 2 parts. There is a command queue and there is a data queue. And they're joined at the hip. So they're dealt with as a single unit, but they're in 2 pieces. And each command has a data size field, and I have a prefix sum unit in the queue manager, so I can pop-off commands automatically calculate data offsets into the data queue, ship that off to the SM or whatever unit, and it can fetch the data at the proper offsets. And the QM, of course, can see the commands and decides who to give it to and what they should do about it. I did not want Uber shaders here. Ideally, I wanted to launch the command as a new, freshly separate compiled program without the burden of Uber shaders. Now, the command queue, size 2 to the n to make it simple. Typically, n is 1. 2 bytes can do wonders, it turns out. So parsing the command queue is not trivial. Every 2 bytes, there's a new command. And let's see. Yeah, ideally, the command queues are in shared memory, in the current architecture at least. And data queues should be in the bigger caches downstream. So a command queue of 2 kilobytes can store 1,000 commands. If you're doing local work creation or consumption in a TPC, maybe a small number of SMs getting involved, then, I mean, shared memory is, I don't know what it is these days, 128, 256, whatever. It's a fair amount of memory. You can store a lot of command queues in local shared memory now without polluting it with data. And yeah, you can have small data queues if you want as well. The queues are also scalar. Because different execution units have different execution widths. The SM loves 32. It's a warp engine. Pixel quads, they work in units of 4 usually. A state update, even to the SM, maybe a width 1 command, change this memory value. And if you emulate a stage, for example, you take the pixel pipe of width 4 and you want to emulate that with an SM shader of width 32, that should be transparent. You shouldn't even know this is happening. So what's done is the queues are all scalar, and therefore they're ordered automatically because it's a scalar queue. You know what comes before what. And the width conversion to the target unit is done automatically by the QM. So parallel push, i.e. a warp, are serialized by the QM in the proper places, and a parallel pop is assembled to whatever execution width you want. So what is the QM at heart? One, it's a small, ideally, database, fixed function unit. There will be a QM everywhere you want queue access because it owns the queue state. You cannot, in the SM or anywhere else, go poking around queues. It's protected memory. Only good for what it's supposed to do. And a queue is owned by one QM. No sharing of state. You know where to go. There's no atomics necessary, no spinning. And let's see, we have covered those two. And there should be an hierarchy of these QMs. You may have local work creation, you may have global work creation or semi-global work creation. And the hierarchy of QMs should have advantageous communication, a back channel for coordinating. Because you may want to, you ask your local queue manager, I want to push on to Q6, and Q6 lives in global memory, then it will do that for you, come back with your pointers, and off you go and store your data. It's not your problem where they are. Now, if you dislike or like hardware diagrams, this is either a nightmare or a dream come true. This is the basic idea of the queue manager. You're living out of L1 or L2. You have SM on the right with a load store. FE here is the front end of the SM. It deals with resource allocation, registers, and the basics of, well, not quite that, but it deals with scheduling and which warps to run, fundamentally. You have a launch unit that deals with resources for the launch, and then the QM on top. And the idea is you have your queue state, you know what's pending work, you have priorities, you pick a queue, you look at the command queue of that queue, you extract some amount of work, and you then decide where that's going to go. You extract the data pointers required to match the commands, ship that off to the SM, let's say in this case, and you launch the work. The SM does the work. It may load from the pop pointers because there's state in the input queue. It'll do its work, it'll open a push via the QM, and it'll store the data with stores, and it'll terminate, and it's done. There is no problem with out-of-order execution here. I'll get to that, why that is. There's a thing called the queue chomper. And this is a really important little subblock. And what it does is it takes the first 64 bytes of a command queue and attempts to pack them into an execution width. Now your commands are powers of 2, but the command itself is just the first 2 bytes. I'll explain what the rest is for. So you extract the first command in the command queue, and it's a 16-bit value. You go 2 bytes forward, get the next one. If they match, and you're allowed to pack them, you're 2 wide. Look at the next one. If it matches, you're allowed to go 3 wide. So you do you basically extract the first command, replicate 31 times, do a broadside compare, and that tells me up to 32 in this case, how many commands can you plot at once. If they're all vertices or pixels, life is good. If it's a state update that says, don't pack me please, then it just does one for you. And it'll launch the work on the SM, for example, with a custom shader that'll do what's necessary. So commands can have payloads, because I like the idea, it's like having a main function in the C program. You can give it input parameters from the command line. I want it to launch work, but I also may want to give it some pre-launch state. Let's say you want to launch a CTA in the middle of your queue. Well, you need some dimensions, I, J, K. How big is the CTA going to need to be? You can pack that into the payload. And then the QM sees that. It'll request the right amount of warps necessary for the problem, and off you go running. And what does a command look like? Well, it's 16 bits. This is a proposal, of course. It's all research. There's a bit called a block bit, which is a really cool bit. You can push commands that cannot be popped. You tag them as saying, do not pop me. And the hardware can have multi-headed pointers, so that the first pointer, head 1 let's call it, is allowed to execute blocked commands, but not to pop them. And the second one can only pop and really get rid of the work if that bit has been cleared. You can execute it twice. The first time, let's say you have a pixel quad. It comes in, and you have this nice ordered list of quads. Why tamper with it? You leave a space in each entry for RGBA, for example. And then you block them, and the SM launch, it gets launched with work. It says, put an RGB in here, please. I want some data for my color. And when you're done with that, clear the bit. And that means the second pointer can now pop the quad in the queue sequence. It just comes off the rear end and off it goes to the ROP. And you can play all kinds of fun games with this, it turns out. You've got to be careful, but it's a fun thing to be able to do. Commands are power of 2, I said. You can have packable or non-packable commands. Some state changes or barriers. You don't want to have 6 barriers packed into a warp. That might be a disaster. There's a command which may go through a lot in the queue to abstract it to something quite interesting. And there's a data count, which also may be an index instead of being an absolute size. And again, chomping is only done for identical commands to build up a width of execution. So a sequence of events, the QM selects a queue for execution. It knows the queue metastate, all the cool stuff on the side, and how busy the execution units are, and it opens a pop onto that queue. You chomp the command queue, you generate data pointers, you send those for execution, and the command queue pop pointers are updated for the next pop, of course. And then execution has read the input data. It informs the QM to close the pop. Now you don't want to free the space out before you load the data from the pop, of course. But you just tell it, I've read the data. You may not close the pop and move on your pointer structure. Execution unit then tells the QM perhaps to open a push. It gets its pointers back where to push it. Data is stored by execution unit. The push is closed. You tell the QM, I'm done with this space. You deal with it, and you're done. And there are 2 tables called push and pop tables. And what happens is when you open a push or when you open a pop, you store the state of that push and pop, the pointer details, into a table entry. And when the pop or push is closed by the execution unit, you mark it as being finished. And then the QM is responsible for walking that table and stitching the pointers back in the order it needs to be. Because if they're out of order terminates, then you can't just take each one and you get holes in your cues, obviously. So I didn't want the warps to waste time spinning, waiting for, am I the next close so I can update the pointers? Get rid of them, move on, execute. Spinning is bad. I don't like wasting cycles, issuing instructions that do no productive work. This is just so NVIDIA graciously allowed me access to some of my old notes. I am retired now. So I've been carefully picking and choosing what I could get access to. There's a lot more to this than I can talk about, because even I don't remember it anymore. But this is some stuff I was fooling with. Yeah, I can draw basic geometry. That's not a problem. This is all Q-based. I can do tessellation. This little thing up here, I actually replaced the texture pipe with a Q in my simulation that does bicubic, map bicubic. So in a real hardware, you would run everything but the texture pipe normally, but you would swap in a shader program for the texture pipe that can do really weird filtering operations if you wanted to. So I had a big C simulator, worked years on that, and then because Dave asked me and I wanted to learn, believe it or not, I never coded CUDA up to this point. I knew all about it from a hardware perspective, but I've never actually used it, and I thought, I should do something about that. So I want a CUDA simulator for all this. And given the current architecture, not this hypothetical future architecture, I use persistent threads, which is a very common technique. And I reserved warp 0 to emulate the Q manager, which I called the queen warp. And the other warps were doing actual execution, and I called them drone warps. And I set up a dispatch table in shared memory, one per warp. And that was the communication channel between the warps and my emulated Q manager. So the pops and push requests went through that table. So the queen could dispatch work to the idle drone warps by writing to the dispatch table. They would get that command execute. If they want to do a push, they put the request back into the dispatch table. QM picks it up, does the whatever queue management stuff is required, returns the answer. Let's see. Yeah, so again, this was with CUDA. I couldn't get access to the standard graphics pipeline units, obviously. But ideally, in some hypothetical future architecture, you would be able to do anything with this. And I did experiment. I ran dozens of SMs in this CUDA simulator. I think I was up to 32 SMs for the fun of it, cooperatively working on queues in global memory. There is that. I knew there was a mistake in spelling or something. So, desired SM enhancements. There's a serious deadlock problem with the SM, obviously, as it does not context switch gracefully. It's a lumbering beast, putting it bluntly. So one thing I would like is to add a new type of warp, which I called the Uber warp. And there would be a small number of these warps, and they would have exclusive reserved assets, resources like registers. There would be a small amount of these because this would be context switchable warps. They would be as lightweight as you could make. And as a result, you can do all kinds of cool stuff quickly and hopefully that's not possible with it. It would be like admin privileged warps that can do really cool stuff, including higher level scheduling. The QM can offload itself to the SM in this design. So it can do a certain amount of queue scheduling in its own backyard, but there may be a very large scheduling adjustment necessary to the load balancing. And it says, SM, run your big shader and tell me how to reprioritize my queues. And every so often it calls that and updates its priorities and back to business it goes. So it would have its own warp for this purpose. And you may want a few of these running around just doing odd tasks for the SM environment. And it's got to have a scheduling priority. Again, when you have a dozen drone warps going or doing something, and you really got to get some QM work done, you don't want to take 1/13 of the issue cycles. You want to run super priority, and I want every instruction I can get so I can get this done as quickly as possible. There's very complicated push command sequences possible because you may have dynamic queue IDs. Nobody knows which queue you're pushing to yet. I actually wrote a fun little program that had 3 different rasterizers in it. One of them dealt with large pixels, triangles, sorry. One dealt with medium triangles, and one dealt with small triangles. So one queue got all the commands that were going to be serviced by 32 triangles per warp. The middle one got triangles that deserved to have 4 threads per triangle. And the big triangles may have gotten 32 threads per triangle, or even multiple warps worth of threads to rasterize the triangles. You can have lots of fun with this stuff. But it's hard to know where the output's going to go, and if your SM10 to context switch, you can deadlock pretty easily. And it's an unsolved problem in general. Yes, you could context switch your way out of it, but there's a few small workarounds I thought about. You can unwind pops that the SM in effect figure out, can I get the resources I need? You have a live block issue coming up here, of course, but you can do some speculative looking ahead and say, this doesn't look good, unwind me, put me back, don't pop me for real, this is just a test, and I can't go forward. Pick somebody else, please, another queue that can go forward. The other one is you can reserve a warp per queue. So no matter what, there's at least 1 warp available for every queue-to-queue transaction. Then you will make forward progress. And if you can't guarantee that, I think you deserve to hang at some point. I mean, you write this stuff in post simulations all the time with CPUs, and you can always hang yourself. Just don't do it at some point. So conclusion, the modern graphics pipeline, it's, I think, about 45 years of age. Kurt would give me the exact birthday when RSGL first was written. He won't remember, he says. He's shaking his head at me. And the API side, RSGL, OpenGL, and DX, and Vulkan, and all this, has, of course, followed the hardware. There's been a mixture of programmable and fixed function units. That's been the traditional approach. And companies are always constrained by time and resources in advancing technology. No matter how big you are, you will not do everything. And if you do, you're in trouble. General programmability requires coordinated change. You can't just swap one unit out. There's no real benefit. You want to do at least a couple, and ideally you do a lot. And the way I think it should be done is you fix the communication plumbing first, so that all the fixed function units feed off a communal, be it queuing system or whatever, and then you can easily swap in code, shaders, to take over for these fixed function units. But even that's a major change, and it wouldn't really make you much money, I suspect, so it's not been all that popular for management to tackle. So without external pressure, it is unlikely to happen, and in that case, I think graphics will eventually move to CUDA. There's just no choice. It's just too limiting in the current graphics pipeline. However, CUDA does need efficient queuing control as well, so I haven't quite given up hope yet. Bibliography of some of the papers, and thank you very much.
Very interesting talk, thanks. So when I was a student, a long time ago, there was a bold statement, I think coming from NVIDIA, that GPUs don't need caches.
Sorry, GPUs?
Don't need caches.
Don't need caches.
And could you give a little bit of history with when NVIDIA decided kind of adopting a full-fledged cache hierarchy?
I would presume in NV50 when CUDA popped up, because John Nichols was really gung-ho about memory spaces and caching and shared memory. I would guess that's when it happened. Before then, yeah, there really wasn't much caching talk, I think. I mean, yeah, you need sure Rock had a mini cache in it somewhere, but I think it was because of CUDA.
Great talk. I'm having a difficult time understanding how queues, QMs, and fixed function hardware work. Is it one queue, one QM, one fixed function? Is it one to many? Is it many to many?
It would be multiple queues managed by one queue manager feeding multiple execution units. And a hierarchy of QMs could deal with global queuing issues. That would be for the local neighborhood. So you can have multiple queues, a real graph, a tree of queues feeding each other, and the QM would walk that for you and issue instructions to make forward progress.
How do line interact with Sebastian Hausmann's graphics API development that he released a few months ago?
I'm sorry, which?
Sebastian Hausmann, he created this non-graphics API.
No, I'm out of the game. I don't follow graphics anymore.
Right, okay. So just in case I have another question. So do you think we are reaching a plateau in terms of year-on-year performance improvements of GPUs, and if we need to
Sorry, I'm gonna have to.
if we need to be more aggressive with changes to the architecture or something like this?
No, I'm skeptical. NVIDIA knows you can smell the dollars. So, no, I love graphics. I spent my whole career doing graphics. I think it's fabulous field. But clearly, the money is not the graphics right now. A responsible company should do what's popular. And that is, AI is huge. It's evolving incredibly fast. And just a fact of life.
And a great talk, loved it. I love the history of things. Fermi, was that the first historical character used in NVIDIA naming convention?
No, it was Fahrenheit a long time ago. Kelvin. They were named after famous scientists. I don't know when that started, I have to admit, but it goes way back.
So thanks a lot. So about this, we've been thinking about all this queuing stuff for quite a few years, right? Maybe started with Grams based on 2009 paper at Kronos. So one concern we always had that how would mortal people work with this and build it on themselves. So what was the idea on the API side?
I guess no comment is the first thing I can say. I felt that they will come was the answer to that. If you can build an efficient system that actually produces real palpable results in performance and flexibility, some bright software guy will figure that out for me. That was not something I lost sleep over. It's about
build it and they'll come.
Well, if the company decided to build something like this, they would staff up a software team at the same time, the architecture team would start, and they would figure this out. I'm not that smart, but that's another answer. I have my limitations. It's a lot of work.
Thank you, great talk. So, I get the sense that it seems like graphics, graphics compute would benefit from some fixed functionality. But there's all this general purpose and, of course, AI compute. I much prefer more programmable architectures. Do you believe that it makes sense to converge these two and have like a AI processing unit and a GPU processing unit that's completely separate?
No, I don't believe that. I believe there is a unified whole that needs to be chased. I don't want to fork it, diverge It's a very small burden. But you can learn from these units what they're doing. Now, you may look at setup and raster and go, oh, it generates pixels. I look at it and go, oh, hey, it's a thread generator. I can do some cool stuff with that. Right? There's two ways of looking at compute versus graphics. They have a commonality that needs to be exploited.
So given this, then, when we hear these companies talk about like the neural engine or these like NPUs, how does that sit with the considerations that you have?
So, to be honest, I am not involved in the AI side at all. I don't know the acronyms even, so I can't really answer. I think it's cool stuff, not that I want to ignore it, but I've been happily retired and trying to get away from it all for a little while, because the last thing I would have wanted when this whole thing broke was to go to the graphics wars and then get into the AI wars, because it would have killed me. Jensen is immortal in some peculiar manner. He can work it's amazing how hard he can work. I can't. I would kill myself if I tried to do too much. And you have to learn your limitations.
One more.
Uh-oh.
Hey Eric, you described the Vertex processor not having any branch instructions, but if you're going to be processing triangles, you've got to be able to clip triangles.
Sorry, when you know a branch, sorry, I didn't say that.
In the original GeForce
going back to the
way back.
GeForce, the GeForce 3 time frame, the original Vertex shader.
And you mentioned there was a state machine and it just advanced through the
It just fell through, yeah.
You didn't say how view frustum calling happened in that case, because that is some kind of...
Well, I wasn't in the TNL engine. That's my answer.
Okay.
It was not a geometry. I mean, yes, it is a geometry engine by name, but it dealt with vertices. It did not deal with geometry aspects of primitives. So it wasn't my problem.
One of the more recent additions to NVIDIA architectures is shader execution reordering, which you can use through callable shaders. So is that something that you would consider?
Reordering? What do you mean?
Shader execution reordering.
What does that mean?
It means you can, so it's meant to be used for ray tracing pipelines, but you can also use it to just invoke a shader from another shader, and then it's a hardware unit that will figure out how to schedule that onto SMs.
Yeah, I don't know about that actually.
Okay, it was introduced in Rafters, but I was wondering if that's something.
Yeah, I was probably in research when that came out. I haven't heard about it. I don't know.
Okay, thanks.
It's a good idea, it sounds like, but the compiler aspects are probably interesting.
Great talk, thank you. You mentioned those Uber warps, and my understanding was that the context switching of warps pretty much worked that way, that they made some of their state persistent in registers. And
Yeah.
also,
Not that I'm in this part of the architecture, but yes, they can be context switched. But when you're dealing with a 32 wide by 128 register bank, context switching is not very agile. And I don't think you can context switch out one warp of a CTA. It's all got to go, I think. There's peculiar limitations. And if you have an emergency request from, let's say, the QM, I got to get this down now, thank you very much. Context switch out that huge pixel shader for me. It's just not practical. It would take, I don't know how many cycles a context switch takes, but it's not pretty, I think.
When you started in 1999, this project, dominant consumer operating system was Windows 95. 98 was just been released, and until Vista in 2007, it was pretty much a far west when it came to writing device drivers. Introducing rapid succession of traumatic changes in the way people would write device drivers. And also there were significant changes in the host hardware, like PCIe and then AGP,
and then
Yeah.
PCI at first.
Yeah, the PC platform was evolving quickly.
Right, exactly. So did any of that affect the way you were thinking or architecting in any shape or form?
No, I don't remember any particular. The Vertex unit was in the graphics pipe. It wasn't the front end unit that dealt with the bus interface. And it didn't have any external memory ports. It was all self-contained, so it didn't really matter what was happening on the periphery of the chip at all. It was a simpler time.
But that has changed, I guess, afterwards, right? More
Yeah,
recent
because now we can run, super duper long vertex shaders, and they have to be able to be, cached. So yeah, it changed. But I think that probably came with MV50, that change. I think before that, the shaders had a limit on its length that grew over the generations, but I think it was still on board. At some point around there, it changed to become a memory that could be a cache. Yeah.
Thank you.
Great. I think Michael had some comments before regarding the banquet here.
So the banquet starts at 6 p.m. in the University Club. So it's a short walk. It's about a 7-minute walk. So we'll see you all there. So the time between now and then, you can do whatever you like, but we generally have to get out of this room. So, so see you at the banquet.
Nerve-wracking is what it is. Let's see, I need my mouse.